Right now, at this exact second you are listening to these words, a single photon is travelling toward this planet from a galaxy you have never seen. It left its star while modern humans did not yet exist. It crossed an emptiness so absolute that during its entire journey, it encountered, on average, less than a handful of atoms. By the time it completes the trip, the civilization that might have launched a probe behind it will be older than every spoken language now alive, and the message it carries, if there ever was one, will arrive at a world that no longer remembers the question being answered. This is what the space between galaxies actually is. Not a gap, not a stretch of darkness, not a corridor that better engines might someday shorten. It is a sentence written into the architecture of the universe itself, and that sentence reads the same in every direction the cosmos chooses to express it. Galaxies are alone. They were born alone, they will remain alone, and the laws of physics, every single one of them, every constant we have ever measured, conspire to keep them that way. You have seen the photographs, deep field images from Hubble, from James Webb, from every great telescope humanity has ever pointed at the deep dark. Galaxies stacked across the frame like jewels on velvet, spirals tilted at impossible angles, ellipticals glowing soft and warm, smudges of light scattered between them like dust catching sunlight in an old room. The images suggest abundance. They suggest a universe full of company. They lie. The truth is something far stranger, far colder, and far more permanent than any photograph has ever been able to show you. And tonight, in the slow, patient way that only deep time can teach, we're going to step into that truth together. We're going to leave the warm glow of our own galaxy behind. We're going to cross over into a place where the rules of distance change, where the meaning of the word neighbour collapses, where light itself becomes too slow to matter, and where the universe finally reveals what it has been hiding behind every beautiful image ever taken. If this kind of slow, careful exploration of the cosmos is the kind of thing you find yourself returning to, do me a small favour and tap that like button. Subscribe if you have not already. It costs you nothing. It tells the algorithm someone is actually listening on the other end of the void, and it lets this channel keep making these long, quiet journeys into the parts of the universe that most stories never have the patience to reach. Now find somewhere comfortable, dim the lights, put away anything that wants your attention. The story we're about to tell needs space to breathe, and it asks only that you breathe with it. We begin where every honest story about cosmic distance has to begin. With the great deception that has shaped every human imagination of space since the first telescope was lifted to the sky. The deception that the universe is full. Chapter 1. The Great Flattening. When you look at any photograph of deep space, something happens to your mind that you do not notice. Your visual cortex, trained across millions of years on the savannas and forests of an entirely terrestrial existence, applies rules that were never designed for the scale of what you are seeing. It assumes that objects close together in the frame are close together in reality. It assumes that the patch of black between two galaxies is a small distance, the way the patch of empty wall between two paintings in a gallery is a small distance. It assumes that the entire image describes a kind of landscape, a scene, a place that could in principle be entered and walked through. None of this is true. The photograph has performed a violence on the cosmos that no one ever explains to you. It has taken a volume of space so enormous that the human brain has no biological equipment to hold it, and it has folded that volume flat. It has crushed billions of light-years of depth into a two-dimensional rectangle that fits on a screen the size of your palm. Every galaxy you see in such an image exists at a different distance. Some are practically next door in cosmic terms, only a few 100 million light-years away. Some are so far that their light began its journey while the universe was still in its infancy, before the first stars had finished forming, when the cosmos was a hot, bright soup of newborn radiation. Between any two galaxies you happen to see touching one another in the frame, there can be entire functioning universes worth of empty space. Consider what the Hubble Ultra Deep Field actually showed us when it was first revealed to the public. The telescope had been pointed at a single small patch of sky, no larger than a grain of sand held at arm's length, for nearly 11 days. The light it gathered was so faint that no ordinary exposure could ever have captured it. And when the image was finally assembled, more than 10,000 galaxies appeared, packed into a frame smaller than your thumbnail. People looked at that image and felt awe. They felt the rightful sense of cosmic abundance. What they did not feel, because no photograph can ever truly convey it, was the depth. Those 10,000 galaxies were not stacked in a small box. They were spread across 13 billion years of cosmic history, scattered through a column of space so deep that the nearest of them sat hundreds of millions of light-years away, and the furthest sat almost at the boundary of what we can ever see. The photograph was beautiful. The photograph was also the most successful illusion in the history of astronomy. To understand what space between galaxies really means, you have to do something almost no one ever does. You have to take the flattened image in your mind and stand it back up. You have to push every galaxy in that frame to its actual depth, separate them by their actual distances, and let the void rush in between them. And when you do that, something terrible happens to your sense of place in the universe. The frame is no longer a crowded jewel box. It is a single thin slice through an emptiness so total that you could remove every galaxy in the image, and the volume of space they occupy would change by an amount too small to measure. This is the first thing you have to accept before any of the numbers can mean anything. The universe is not full. It has never been full. The photographs have shown you the rare exceptions to the rule, and the rule is, and has always been, emptiness. But to feel the weight of the emptiness, you first have to feel the weight of the structures it surrounds. You have to understand how vast a single galaxy actually is, because the distance between galaxies is measured in multiples of that vastness. And until you can hold the size of one galaxy in your mind, the number 2.5 million light-years will pass through your ears as just another number. So we begin closer to home. We begin with the only galaxy you will ever, in any meaningful sense, live inside. Chapter 2. The Country Made of Stars. If you could leave this planet right now and rise straight upward, perpendicular to the surface, perpendicular to the orbit of the moon, perpendicular to the plane of every planet that wheels around our sun, and just keep climbing, the first thing you would notice is how quickly the familiar disappears. The Earth shrinks to a pale dot within an afternoon at the speed of a fast spacecraft. The sun follows soon after, becoming first a coin, then a bright star, then merely the brightest of many. By the time you have climbed for centuries, the entire arrangement of our solar system, every planet, every comet, every distant icy body in the Oort cloud, has collapsed into a single point of light that you can cover with the tip of your finger. But you're not yet anywhere. You have not left home. You've only just begun to perceive what home looks like from outside. Keep going. climb for 10,000 years at the speed of light. The point of light that contains everything you have ever known and everyone you have ever loved is now buried among other points of light, all of them similar, none of them special. The arrangement of those points has texture. A faint structure begins to emerge. You see a flattened spiral, glowing soft and golden, with a bright concentrated centre and long curving arms reaching outward like the slow stretch of a sleeping cat. The arms are dotted with brilliant blue knots where young stars burn fast and hot. The centre is dense with old red and yellow suns crowded together so tightly that from a distance they melt into a single warm pool of light. Dust lanes thread between the arms in dark rivers. The whole structure rotates so slowly that no eye could ever detect the motion, but each star in it traces an enormous orbit around the centre, returning to its starting position only after hundreds of millions of years have passed. This is the Milky Way. This is what your galaxy looks like from far enough away to actually see it. And to call it large is to insult the word large. There are at least 200 billion stars in this single structure. Some recent surveys suggest the true number may approach 400 billion. Every one of those stars is a sun. Some are smaller and cooler than our own. Some are larger and hotter. Some are calm and steady, burning for 10 or 20 billion years. Some are short-lived monsters that flare into existence, blaze for a few million years, and then collapse into supernovae that briefly outshine entire galaxies. Around many of these stars there are planets. Around many of those planets there are moons. There are asteroid belts, comet clouds, frozen bodies drifting in long elliptical orbits, rogue worlds wandering between stars without any sun to call their own. The total number of distinct astronomical objects contained inside the Milky Way is a number so large that human counting falls apart trying to express it. And all of this, every star, every planet, every moon, every drifting fragment of ice and rock, fits inside a disk roughly 100,000 light-years across. Some measurements that include the outer halo and the surrounding dark matter envelope push that figure up to 200,000. Either number is a horror. A light-year is the distance that light, the fastest thing in existence, travels in one Earth year. Light moves at 300,000 kilometers per second. In 1 second it could circle the Earth 7.5 times. In a single minute it travels far enough to reach the Sun. In an hour it crosses the orbit of Jupiter. In a day it covers a distance greater than 10 times the orbit of Neptune. In a year, that same beam of light has travelled approximately 9.5 trillion kilometres, a distance so vast that the human mind genuinely cannot picture it, only abstract it into a symbol. Now multiply that distance by 100,000. That is the width of the country you live in. Not the country of your nation, not the country of your planet, not the country of your solar system. The country of your galaxy, the basic unit of cosmic geography. If you fired a beam of light from one edge of the Milky Way and aimed it at the opposite edge, the photons would travel for 100,000 years before they arrived. When that beam was launched, our species had not yet domesticated fire. The cave paintings in Lascaux had not been imagined. The first agricultural villages, the first cities, the first written languages, every religion, every empire, every war, every poem, every recorded act of human history had not happened and would not happen for tens of thousands of years. By the time the light reaches the other side, civilizations across our planet have risen, flourished, collapsed, and been forgotten more times than any of them could have suspected. That is the size of a single galaxy. One photon, travelling at the absolute speed limit of the universe, crossing one structure. 1,300 human lifetimes laid end to end is barely enough time for the trip. This is the ruler with which we now have to measure the gap between galaxies. And the moment you grasp how long that ruler is, the moment you accept that the basic unit of cosmic distance is already 100,000-year flight at light speed, the numbers that follow begin to feel less like statistics and more like sentences. They start to weigh something. They start to mean something. They start to settle in your chest the way deep cold settles into a stone. Because the closest neighbour to this country of stars, the closest other galaxy of comparable size to our own, is 25 times further away than the country itself is wide. Chapter 3. The Smudge That Is a Nation. Step outside on a clear autumn evening in the Northern Hemisphere. Find a place where the lights of cities cannot reach you. Let your eyes adjust to the darkness for at least 20 minutes. Look toward the constellation we call Andromeda. Just above and to the side of the chain of stars that marks the constellation's body, you may see, if the sky is dark enough and your eyes are patient enough, a small grey smudge. Faint, oval, easy to miss. The kind of thing your peripheral vision picks up better than your direct gaze. That smudge is not a cloud. It is not a nebula inside our own galaxy. It is not a defect of your vision or a trick of the atmosphere. That smudge is the most distant object the unaided human eye can perceive without any equipment whatsoever. It has been visible to every generation of humans who ever lived. It was visible to the first people who learned to look up and wonder. It was visible to the astronomers of ancient Persia who first catalogued it more than 1,000 years ago. It was visible to Galileo, to Newton, to Kepler, to every stargazer who ever turned their attention to that particular patch of sky. And until 1923, when Edwin Hubble used the new Hooker telescope on Mount Wilson to measure the distance to a single pulsing star inside it, no human being on this planet understood what that smudge actually was. What that smudge actually is another country. Another country of stars, not a small cluster, not a satellite, not a remnant or a clump or a wisp. A full nation of suns, larger than our own, older than our own in some respects, with its own central black hole, its own spiral arms, its own stellar populations, its own complex history of mergers and collisions and quiet, patient evolution. The Andromeda Galaxy, in every meaningful sense the closest thing the cosmos has given our galaxy to appear. 1 trillion stars live inside that smudge. Read that number slowly. 1 trillion. Roughly 2.5 to 5 times the population of our own galaxy. If you took every grain of sand on every beach on every coastline of every continent on Earth, the total number would still be 1,000 times smaller than the number of stars in Andromeda alone. Each one of those stars is its own private sun, with its own private timing of birth and death, its own private orbit around the galactic centre, its own private retinue of planets that may or may not exist, and may or may not harbour anything resembling life or chemistry, or even the simplest stirrings of weather. Every one of those stars is a complete world unto itself in the way that our sun is. They number in the trillions. In January of 2025, the Hubble Space Telescope completed and released a mosaic image of the Andromeda Galaxy that took more than a decade of careful observation to assemble. Over 600 separate exposures were stitched together into a single enormous picture, and that picture resolved approximately 200 million individual stars across the galaxy's face. 200 million, each one a pinprick of light in the mosaic, each one a real ongoing thermonuclear reaction many trillions of kilometers away. And the entire population of stars that Mosaic captured represented less than 1/5 of 1% of the galaxy's total stellar census. Most of Andromeda's stars are too faint, too crowded, or too obscure to be picked out individually. The Mosaic showed us the brightest, most photogenic fraction of a population that runs into the trillions. The disk of Andromeda spans roughly 200,000 to 260,000 light-years from one edge to the other. It is comparable in size to our own galaxy, and by most modern measurements probably slightly larger. Inside that disk there are spiral arms, dust lanes, star-forming regions, ancient globular clusters older than the planet you stand on, dwarf companions orbiting in faint loose halos, streams of stellar debris from past collisions with smaller galaxies that wandered too close and were absorbed. The whole structure is held together by gravity and by a vast invisible halo of dark matter that surrounds and embraces the visible stars like a deeper ocean wrapping a luminous one. At the centre of Andromeda there sits a single supermassive black hole. Its mass is currently estimated at well over 100 million times the mass of our Sun. It is silent now, mostly. It feeds slowly, but it dominates the gravitational character of the galactic core, holding the densest swarm of stars in tight orbits around it, anchoring the entire spiral. This is what is sitting across the sky from you when you find that faint grey oval in the constellation Andromeda. Not a wisp, not a small thing. A complete civilization of stars more populous than every star in our own galaxy, combined and multiplied. An entire other Milky Way, only slightly larger, slightly older, and entirely separate. And it is 2.5 million light-years away. Chapter 4. The Weight of a Number. There is a danger in numbers like 2.5 million light-years. The danger is that they slide past the mind without leaving a mark. You hear them, you nod, you move on. They sit inside the ear for a second and then drift away with all the other large numbers you have heard in your life, and your brain treats them as roughly equivalent to 2,000 or 200,000 or 2 billion. The mind simplifies. It has to. The mind is not built for these magnitudes. So we're going to take this number apart slowly, and we're going to put it back together in pieces small enough for the mind to actually weigh. A light year is roughly 6 trillion miles. That is 6 followed by 12 zeros. To begin to feel that number, consider that the distance from this planet to the Moon, the distance our species took 3 days to cross during the Apollo missions, is approximately 240,000 miles. A single light year contains 25 million of those moon trips, laid end to end. If every human being on Earth, all 8 billion of us, went to the Moon and back once each, and we summed up the total mileage of every trip, we would still need to multiply that combined journey by more than 3,000 to equal a single light year. Now multiply a single light year by 2.5 million. Stop. Sit with that for a moment. We just multiplied a number that already broke the mind by a factor of 2.5 million. The result is approximately 15 quintillion miles, 15 followed by 18 zeros. That is the distance between our galaxy and the galaxy we casually call our neighbour. The number has so many digits that writing it out provides no useful information. It exists in a region of magnitude where human intuition simply does not function. So let us try to translate it into time. Time is the dimension the mind can almost handle, because we live inside it, even if only for a few decades each. In December of 2024, the Parker Solar Probe, a small unmanned spacecraft built by NASA, made the closest approach to the Sun any human-made object has ever achieved. As it whipped past the solar atmosphere, harnessing the Sun's gravity to accelerate, the probe reached a velocity of approximately 430,000 miles per hour. This is the current speed record for any machine our species has ever built. At that speed, you could travel from London to New York in roughly half a minute. You could circle the planet entirely in less than 4 minutes. You could reach the moon in well under an hour. By every standard of human engineering, the Parker Solar Probe is the fastest thing we've ever made. At that speed, the journey to Andromeda would take approximately 4 billion years. Not 400 years, not 4,000, not 4 million. 4 billion. That is roughly the age of the planet you're standing on right now. The Earth is approximately 4.5 billion years old. If our most ancient ancestors of the rock and dust kind, the first molten droplets that coalesced into a young proto-Earth, had somehow built and launched the Parker Solar Probe at the moment of the planet's birth, the probe would only now, 4.5 billion years later, be approaching the outskirts of the Andromeda Galaxy. 4 billion years is longer than complex life has existed on Earth. It is longer than oxygen has been a major component of our atmosphere. It is longer than continents have moved into their current configurations. It is longer than every event our species can name, every event our planet can record, every event our galaxy has produced inside the lifetime of our solar system. And that is the time required to cross the gap to our closest galactic neighbour at the fastest speed we have ever managed to make anything move. You begin to understand why the number 2.5 million light-years had to be taken apart. Even at the speed of light itself, the absolute speed limit of the universe, the journey takes 2.5 million years. 2.5 million years ago, our ancestors were not yet anatomically modern. The genus Homo had only recently emerged in Africa. There were no spoken languages we would recognize. There was no agriculture, no writing, no architecture, no metal, no domesticated animals, no fire that we knew how to start ourselves, no clothing, no art, no music, no religion, no philosophy, no science. The thing that would eventually become us had only just begun to exist as a creature distinguishable from its ancestors. When the photons currently arriving in your eyes from the Andromeda Galaxy began their journey, none of what we now call human existed. By the time those photons completed their trip, every empire that has ever been built and lost was already a memory. The light that the Andromeda Galaxy is shining on you tonight was emitted before the wheel was invented and arrived after the wheel was reinvented as the rotor of a jet engine. The transit was longer than the entire arc of our species, and Andromeda is the close one. Andromeda is the next-door neighbour. Andromeda is the easy target, the friendly destination, the practice run for any cosmic ambition. Beyond Andromeda, the distances begin to multiply in ways that do not fit inside any unit we've ever named. But before we leave Andromeda, there is one more thing about it that has to be said. Because it is the only thing across the entire universe that is actually doing something we can directly measure with respect to our own galaxy. It is moving toward us. Andromeda is approaching the Milky Way. This is not a guess. This is not a theory. This is a directly measured radial velocity, observed for over 100 years through the careful analysis of how the light from Andromeda's stars is shifted toward the blue end of the spectrum. The galaxy is currently closing the distance between us at a velocity of roughly 250,000 miles per hour. That is faster than any human-made object has ever been recorded moving by a considerable margin. Every second, the gap between our galaxies shrinks by about 70 miles. Every year, it shrinks by enough to span the distance from our Sun to nearly the orbit of Uranus. And yet, at that speed, the journey will still take billions of years. In the original 20th century version of this story, the answer seemed clear. The two galaxies would meet in roughly 4 to 5 billion years and merge into a single enormous structure that astronomers nicknamed Andromeda. The collision was treated as a near certainty. But astronomy is not a discipline that respects certainty for long. In 2025, a major reanalysis of the relative motion of the two galaxies, incorporating new data from the Gaia spacecraft and refined measurements of the gravitational influence of the Large Magellanic Cloud and the Triangulum Galaxy, suggested that the probability of an actual direct collision within the next 10 billion years might be closer to 50%. A subsequent paper in 2026 incorporating the most recent proper motion measurements pushed the probability back up to around 90% and placed the most likely collision time at roughly 6.5 billion years from now. The exact outcome remains an open question. The story is still being written, but the broad truth, regardless of how the details settle, is this. The Milky Way and Andromeda are gravitationally bound. They are not flying apart. The expansion of the universe that drives most galaxies away from one another has no power over the relationship between our galaxy and our closest large neighbour. We are held together by mutual gravity. We're caught in a slow embrace that has been tightening for billions of years and will continue tightening until something finally happens between us. And that gravitational marriage, the closest thing the cosmos has ever offered our galaxy in terms of a confirmed partner, plays out across a distance that even light cannot cross in the lifetime of our species. That is what closeness means at the scale of galaxies. That is what neighbour means in the language of intergalactic geography. Two civilizations of stars locked in mutual gravitational attraction, falling slowly toward an inevitable union, separated by a void so wide that the actual encounter will not happen until after our sun has died, after the earth has been swallowed, after every form of life that has ever existed on this planet has long since been forgotten by whatever continues to exist in their place. This is the close one, the friendly one, the galaxy that is actually coming for us. Everything else is going the other way. Chapter 5. The Quiet Family. Before we leave the relative warmth of our cosmic neighbourhood and step out into the deep emptiness beyond, we should look around once more at the family we belong to. Because most people, when they imagine the Milky Way's place in the universe, picture only the Milky Way itself, possibly Andromeda as a partner across the gap, and then a vague, swirling abundance of other galaxies somewhere in the distance. The reality is more textured and more lonely than that picture admits. We belong to a small, loose collection of galaxies that astronomers call the local group. The name is matter of fact, the way an English village is named for the bend in the river it sits beside rather than for any feature of its own. The local group is simply the gravitational gathering of galaxies we happen to share a region of space with. It contains, by current counts, approximately 130 to 140 distinct members, with new ultra-faint dwarf galaxies still being discovered every year as surveys like Gaia and instruments like the James Webb Space Telescope finally become sensitive enough to detect them. 140 members sounds like a crowd. It is not. Of those 140 members, the vast majority are dwarf galaxies so small and so dim that no civilization living inside one of them, if such a thing exists, would even necessarily realize it lived inside a galaxy at all. Some of them contain only a few million stars, scattered loosely across volumes of space that would barely qualify as a galactic core for a larger spiral. Most of these dwarfs orbit the Milky Way or Andromeda as satellites, trapped in long, slow trajectories around their parent galaxy, the way a moon orbits a planet. They are essentially gravitational debris, fragments of an earlier era of galactic formation that never grew into anything larger, now bound forever to the company of their larger neighbours. 3 of the local group's members are large enough to be called proper galaxies in the full sense: the Milky Way, Andromeda, and, considerably smaller than either, the Triangulum Galaxy, which contains roughly 40 billion stars and sits about 2,700,000 light-years away from us, slightly further than Andromeda. Triangulum is currently considered the 3rd largest member of our local group, though some recent measurements suggest it may be gravitationally bound more tightly to Andromeda than to the group as a whole, possibly orbiting Andromeda over enormous timescales. After these 3, everything else is small. Dwarf elliptical galaxies, dwarf spheroidal galaxies, irregular galaxies that look like puffs of cosmic smoke caught in a slow gravitational current. The Large Magellanic Cloud, visible from the southern hemisphere as a faint detached patch of the Milky Way, sits about 160,000 light-years away and is currently being slowly consumed by our galaxy's tidal influence, its outer stars stretched into long streams that wrap around the Milky Way's halo like silk threads pulled from a tapestry. The Small Magellanic Cloud, a smaller companion, sits about 200,000 light-years out. The Sagittarius Dwarf Elliptical, even closer in at roughly 70,000 light-years from our galactic centre, is being actively torn apart by our gravity, its stars dispersing into the Milky Way's disk in long, graceful filaments that astronomers can still trace today. The total volume of space that this entire family occupies is enormous. The local group from one edge to the other measures roughly 10 million light-years across. That is 100 times the diameter of the Milky Way itself. 100 times the size of the country we have just spent so many minutes trying to wrap our minds around. Imagine standing in your house. Imagine being told that the closest other building is 100 house lengths away, not 100 feet. 100 entire houses, laid end to end between you and your nearest neighbour. That is the kind of spacing we're describing when we talk about the structure of our local group, and our local group is one of the densest galactic environments anywhere in our cosmic vicinity. There is nowhere else in the nearby universe where galaxies are packed any tighter than this, and the gaps between members of the family already make the word neighbour seem like a kind of cruel joke. When astronomers map the 3-dimensional structure of the local group, what they find is not a swarm or a cluster, but something more like a dumbbell. 2 larger concentrations of galaxies sit at opposite ends of the structure. One end is anchored by the Milky Way and its swarm of satellite dwarfs. The other end is anchored by Andromeda and its own retinue of smaller orbiting galaxies. Between these 2 anchors, a sparse population of isolated dwarfs drifts through the gravitational field of both giants. Too far from either centre to feel fully at home, too small to anchor a community of their own. The space connecting the 2 ends of the dumbbell is mostly empty. There are a few scattered dwarfs threading the gap, but mostly the connecting volume is intergalactic darkness, traversed only by gravity itself. Even within this gravitationally bound family, the distances are crushing. The Sagittarius dwarf, our closest satellite, is 70,000 light-years from the galactic center, which means even light needs 70,000 years to bring news from that companion to our own core. The Large Magellanic Cloud is more than 160,000 light-years away, the Small Magellanic 200,000, the Andromeda Galaxy 2.5 million, and these are the close ones. These are the galaxies we share gravity with, the galaxies our own structure pulls on directly, the galaxies that in some long unwritten chapter of the universe will eventually merge with us. The next nearest significant non-satellite galaxies beyond the immediate orbits of the Milky Way and Andromeda. Things like the irregular galaxy NGC 6822, the small spiral IC 1613, the dwarf galaxy WLM, sit at distances of 1.5 million, 2 million, 3 million light-years. They are members of our local group only in the loosest sense. Their gravitational connection to our galaxy is so faint that they barely register, drifting through the outer halo of the family at speeds that make their relationship to us almost a coincidence. Once you accept that even the inside of our family is mostly empty, that even our gravitationally bound community is a sparse, mostly silent dumbbell of dwarf galaxies suspended in deep space, the next step out of the family becomes much harder to face. Because beyond the local group there is no other family for an immense distance. The nearest comparable gathering of galaxies, the next association of structures that could be called a community, lies tens of millions of light-years away, on the far side of an enormous gulf of effectively empty space. To leave the local group and step out into that gulf, even in the imagination, is to leave behind every gravitational thread that still connects our galaxy to anything else. Beyond the local group, the universe has no neighborhoods. There are clusters and superclusters and walls and filaments, vast and beautiful and unimaginable in their own right. But the very fact of cosmic expansion ensures that none of those distant communities are bound to us. They are not coming closer. They are not waiting for us. They are receding, accelerating away into a darkness that grows wider every second. And the moment you cross the boundary out of the local group, you enter the dominant feature of the universe. Not galaxies, not clusters, not stars or quasars or any glowing thing at all. You enter the void. Chapter 6. The place where nothing lives. Picture yourself, just for a moment, at the geometric center of the gap between the Milky Way and Andromeda. You're 1.25 million light-years from either galaxy. Your suit is functioning, your eyes are open, your instruments are recording. You've arrived at the closest thing the universe has to a midpoint between two countries of stars. Look behind you. The Milky Way is there, but not the Milky Way you've ever seen. There is no broad band of starlight arcing across the sky, because you're no longer inside the disk. From here, our galaxy appears as a single pale oval, smaller than your outstretched thumb at arm's length. It is featureless from this distance, a soft uniform glow with no individual stars resolved within it, a kind of luminous fingerprint on the darkness. If you stare at it long enough, you might be able to make out the faintest hint of structure, perhaps the spiral arms or the brighter central bulge, but only if your instruments help you. To the naked eye, it is just a smudge, the same kind of smudge that Andromeda appears as from Earth. Now turn around. Andromeda is there too in the opposite direction, identical in its presentation, Another small pale oval, soft and quiet, hanging in the dark. Two countries of stars suspended at the opposite ends of a gulf so wide that from your position at the centre, both look exactly like that faint patch of grey light you can see on a clear autumn night from your back garden on Earth. Now look in every other direction. Nothing. And nothing in a sense that goes far beyond the meaning the word usually carries. Not nothing as in a dark empty room where you still hear walls and breath and the small sounds of being alive. Not nothing as in the dark of a closed eye where the ghost of light still lingers behind the lid. This is structural nothing. This is the absence of every reference point that has ever defined what it means to exist in a place. There are no stars in any of the directions you look. Not one. The nearest individual star in any direction is so far away from you that it cannot send enough photons to register as a point of light. You float in a darkness so complete that without the two faint oval smudges behind and ahead, you would have no way of knowing which way was forward or backward, which way was up or down, where you had come from or where you were going. And here is the strange thing. Your instruments confirm something even your eyes cannot quite grasp. You're not floating in nothing. You're floating in something. There is matter here, just not enough to make any sensible difference. The space between galaxies is not perfectly empty. There is gas, there is dust, there is a hot tenuous plasma that astronomers call the warm hot intergalactic medium, a vast diffuse haze of ionized atoms stretched across the cosmic volume at temperatures of hundreds of thousands or even millions of degrees. This material was missing from our understanding of the universe for a long time. For decades after the cosmic microwave background told us exactly how much ordinary matter the early universe had produced, astronomers could only find about half of that matter inside the visible structures, the galaxies and clusters and gas clouds. The other half had simply vanished. In the 2010s and 2020s, careful observations of distant quasars, absorption lines from highly ionized oxygen and other heavy elements, and dispersion measurements of mysterious fast radio bursts finally pinned down where the missing baryons had gone. They had not gone anywhere unusual. They had been spread across the intergalactic medium so thinly that no instrument before could detect them. How thinly? Approximately 1 atom per cubic meter. Sometimes a few atoms in the densest filamentary regions, sometimes less than 1 atom across many cubic meters in the deepest voids. To understand what 1 atom per cubic meter means, consider the air in the room where you're listening to this. That air contains roughly 25 trillion molecules in every cubic meter. Not trillion, trillion. A number with 25 zeros after it. That is the air your lungs are pulling in and pushing out right now. Take that air. Empty all of it out of 1 cubic meter of space, every single molecule, until only 1 atom remains. That is the density of the warm, hot intergalactic medium between galaxies. The vacuum chambers used in the best particle physics laboratories on Earth, the most carefully evacuated artificial vacuums humanity has ever produced, contain on the order of 10 trillion molecules per cubic meter. Intergalactic space, the place you're now imagining yourself floating in, is approximately 10 trillion times emptier than that. There is no laboratory environment that comes close to it. There is no human technology that can manufacture this kind of vacuum. The space between galaxies is the most perfectly empty natural environment the universe is capable of producing, and the strangest part is the temperature. The intergalactic medium, despite containing almost nothing, has a temperature. The particles that do exist in it, sparse as they are, are moving fast. Many of them are moving at speeds equivalent to temperatures of millions of degrees, hotter than the surface of the sun. This sounds impossible. How can a near vacuum be so hot? The answer lies in what temperature actually measures. Temperature is the average kinetic energy of the particles in a substance. With so few particles per cubic meter, there is no meaningful transfer of heat from the medium to anything you might place in it. You could float in intergalactic space, surrounded by particles moving at temperatures hotter than the sun, and the medium would not warm your suit by a measurable amount. The particles simply pass through your local volume too sparsely to deposit any meaningful energy. You would freeze. You would die of cold while suspended in a vacuum technically hotter than a star. This is the environment that fills the gap between every galaxy and every other galaxy. Not a corridor, not a passage, not a thinned but navigable expanse. A vast structural absence with a faint scattering of impossibly diffuse, impossibly hot, impossibly empty plasma drifted through it. The kind of place that breaks the categories we usually use to describe the world, where the words full and empty no longer mean what they ought to mean, where hot and cold lose their connection to anything a body could feel, where the act of describing the place at all begins to feel like an exercise in technical labels rather than honest perception. And this place is enormous. Within our own local group, where the warm, hot intergalactic medium is at its densest because we're inside a small, relatively concentrated patch of cosmic structure, the gap between the Milky Way and Andromeda alone covers a volume of space many times greater than every star, every planet, every nebula, every dust cloud, every meaningful object inside both galaxies combined. The volume is mostly empty. The mass inside it, even after we account for all the warm, hot intergalactic medium, is functionally zero by comparison. Step outside our local group into the wider universe, and the situation gets worse. Chapter 7. The Foam of the World. For a long time, astronomers assumed that galaxies were sprinkled through the universe more or less randomly, the way grains of sand are scattered across a wide-open beach. The idea of a structured cosmos on the larger scale seemed implausible. The universe, after all, had emerged from a hot, smooth Big Bang, and on the very largest scales it ought to remain roughly uniform, smeared out by the random walk of cosmic history into a kind of homogeneous froth of galaxies suspended in expanding space. That assumption did not survive the data. Beginning in the late 1970s and accelerating through the 1980s, with the first systematic redshift surveys, astronomers began to map the three-dimensional positions of galaxies in space. They measured how fast each galaxy was receding from us, which told them how far away it was, and they plotted the resulting three-dimensional locations on enormous maps. The maps revealed something nobody had quite expected. Galaxies were not scattered. They were organized. The universe, it turned out, had a structure, a vast, intricate, three-dimensional network that traced the largest pattern existence had ever revealed about itself. Galaxies clustered along narrow filaments of matter, the way droplets of water cling to the strands of a spider's web. The filaments met at dense nodes where the largest gatherings of galaxies sat, places now called galaxy clusters and superclusters. Between the filaments, separated by walls of slightly less dense material, lay vast spherical regions of nearly empty space, cosmic voids, bubbles of nothing, some of them hundreds of millions of light-years across. The pattern, when you map enough of it, looks unmistakably like foam, or like a sponge, or like the bubbly residue inside a cosmic cup of coffee that no one ever bothered to wash. The galaxies of the universe are not spread out evenly. They cling to the surfaces of vast bubbles of darkness, and the bubbles, the voids themselves, occupy roughly 80% of the universe by volume. 80%. You have to let that number settle into you. Of all the volume the observable universe contains, only 20% of it has any meaningful matter inside it at all, and that 20% is itself mostly empty. Inside the filaments and walls and clusters where galaxies cluster together, the matter is still spread incredibly thin. The galaxies themselves are pinpricks of structure inside thin ribbons of structure, inside a universe whose dominant feature is the empty bubble. This is the cosmic web, the largest pattern science has ever discovered. The shape of everything. Now consider what this means for a galaxy. Any galaxy. Pick the Milky Way, pick Andromeda, pick a galaxy somewhere in the Virgo cluster. The cosmic web means that a galaxy, on average, sits on the thin surface of an enormous empty bubble. In one direction, the galaxy looks out along its filament and sees other galaxies along the same thread, separated by distances of millions or tens of millions of light years. In another direction, the galaxy looks across the void into the empty bubble it borders and sees almost nothing for hundreds of millions of light years. The same galaxy, depending on which way you turn it, is either embedded in a thin chain of cosmic community or marooned on the edge of an emptiness so vast that the next galaxy in that direction may not exist within any realistic travel distance. The largest cosmic voids known to astronomy are difficult to describe without losing the listener. The Bhuta's void, discovered in 1981 by Robert Kirshner and his collaborators, is a roughly spherical region of nearly empty space, about 330 million light-years in diameter. It sits about 700 million light-years away from us. Inside that enormous volume, astronomers have detected approximately 60 galaxies. The cosmic average would predict 2,000 or more in a region that size. The void is so empty that if our own Milky Way had happened to be positioned at its centre, we would not have discovered the existence of other galaxies until well into the 20th century, because nothing else would have been visible from inside that enormous bubble. The very idea that the universe contained other galaxies would have seemed absurd to any civilization living inside the Bhuta's void, because the universe around them would have looked exactly like a single galaxy, floating in infinite empty space. And the Bhuta's void is just one of many. The KBC void, named after the astronomers Keenan, Barger and Cowie, who proposed its existence, is the region in which our own galaxy may actually reside. It is a slightly underdense bubble approximately 2 billion light-years across, with a density some 20% lower than the cosmic average. The Eridanus supervoid, sometimes nicknamed the Great Cold Spot of the cosmic microwave background, is another candidate cosmic underdensity that may extend across more than 1 billion light-years. These regions are not anomalies, they are the rule. The universe is made mostly of voids, the galaxies the exception, the residue left behind when gravity drained the matter out of the empty regions and concentrated it along the thin walls and filaments where structure could form. This architecture is not accidental. It is the direct consequence of the way the universe began. In the first few 100,000 years after the Big Bang, the matter content of the universe was almost perfectly uniform. The cosmic microwave background, the radiation we still detect today as a faint glow filling the sky in every direction, was emitted when the universe was approximately 380,000 years old, and the density variations encoded in that radiation were tiny. less than 1 part in 100,000. The early universe was nearly featureless, varying from one region to another by amounts so small that the imperfection was almost imperceptible. But gravity is patient. Gravity does not need much to work with. A region of space that was even 1 part in 100,000 denser than its surroundings would pull in additional matter from the regions around it, growing slightly denser over time. The regions it pulled matter from would grow slightly emptier. Over hundreds of millions of years, the dense regions grew dense enough to begin collapsing into the first stars and galaxies. The emptier regions, drained of their matter by the gravitational pull of their denser neighbours, expanded into the voids we see today. The cosmic web is gravity's biography. Every filament traces where matter accumulated. Every void traces where matter was siphoned away. The structure and the emptiness are 2 halves of the same process. You cannot have one without the other, and here is the truly devastating part. The voids are not static. They are growing. Cosmic expansion stretches all of space, but in the dense regions where gravity dominates, the local effect of expansion is suppressed. Galaxy clusters remain gravitationally bound. The galaxies inside them do not fly apart. But inside the voids, where matter is too sparse for gravity to resist the expansion, dark energy drives the local expansion of space at an accelerating rate. The voids are getting bigger every second. The walls between them are getting thinner. The filaments are stretching. The cosmic web is dissolving slowly under the relentless pull of cosmic expansion, and the only thing the universe is gaining as the web unravels is more void. This is what the universe is becoming: more empty, more structureless, more dominated by the very absence that already defines its larger scale architecture. And the galaxies, the rare beautiful exceptions to the rule of emptiness, are being pushed further and further apart with every passing instant of cosmic time. The implications of this for any hope of intergalactic travel or communication or contact are not subtle. They are catastrophic, and we have to face them now, fully and honestly, because they are the final wall that turns the cosmos from a vast playground into a cosmic sentence of solitary confinement. Chapter 8. The Wall Made of Light. Imagine for a moment that humanity has overcome every challenge. Imagine the engineering has been solved. Imagine that we have built somehow, by means we cannot currently conceive, a spacecraft capable of travelling at a meaningful fraction of the speed of light. Not 10%, not 50%, say 90%. 9/10 of the absolute speed limit of the universe, the velocity beyond which nothing made of matter can ever quite reach. We have built such a ship. We have figured out how to power it. We have figured out how to keep its passengers alive. We have figured out everything. Now point that ship at the Andromeda Galaxy and fire the engines. At 90% of the speed of light, the journey to Andromeda will take, as measured from Earth, approximately 2,800,000 years, roughly the same as the speed of light alone, only slightly longer because we're travelling at 90% rather than 100%. But here is the strange and merciful gift of relativity. The crew on board the ship does not experience that full time. As you approach the speed of light, time on board slows down relative to time in the rest of the universe. The closer you get to light speed, the more aggressively that slowing happens. At 90% of light speed, time dilation compresses the journey by a factor of approximately 2.3. The crew on board experiences not 2,800,000 years, but roughly 1,200,000 years. 1,200,000 years. That is the experience duration of the trip, for the people inside the ship, even with the gift of time dilation working in their favour. That is still longer than the entire span of modern humans as a species. The crew that arrived at Andromeda would be no kind of descendants of the crew that departed in any meaningful sense. They would be a different species. They would have evolved across more generations than have ever existed in human history. The civilization that launched the ship would have transformed beyond recognition or vanished entirely several times over. The message could be sent. There would be no one to receive the reply. What if we push the ship faster? 99% of light speed. Time dilation compresses experienced time by a factor of approximately 7. The crew now experiences roughly 350,000 years, still longer than the entire span of modern humans, 99.9% of light speed, time dilation factor of approximately 22. Crew experience reduces to roughly 113,000 years. Better, but still longer than recorded civilization, by several orders of magnitude. 99.99% of light speed. The crew now experiences only tens of thousands of years. But notice what has happened to the energy requirements. To accelerate even a single kilogram of mass to 90% of light speed requires an energy expenditure equivalent to nearly the total annual energy consumption of a small nation. To accelerate it to 99% requires several times that. To accelerate it to 99.99% of light speed requires energies that approach the entire output of a modest star over an extended period. And we're talking about a single kilogram. A real spacecraft with passengers and shielding and life support and the fuel needed to slow down again on the other side would require energy budgets that exceed the total output of human civilization across all of recorded history. The numbers do not just get large, they become unphysical. We're not talking about engineering challenges that incremental progress could solve. We're talking about energy requirements that violate every reasonable extrapolation of what civilization can produce. And this is to reach the closest large galaxy. This is to make a one-way trip that would take longer than our species has existed, even at speeds so close to light that the energy required becomes absurd. For any galaxy beyond Andromeda, the situation deteriorates rapidly. The Virgo cluster, the nearest major gathering of galaxies, sits 54 million light-years away. At 90% of light speed, the experienced journey time would be approximately 26 million years. That is longer than primates have existed on Earth. The Coma cluster, 320 million light-years away, would require an experienced journey of roughly 150 million years even at relativistic speeds. That is older than the dinosaurs. But the truly devastating barrier to intergalactic travel does not come from energy or time dilation or distance directly. It comes from something even more fundamental. The space between galaxies is not a fixed quantity, it is growing. This is the third great obstacle, and it is the wall that no amount of engineering can ever overcome. Because the wall is not made of matter. The wall is made of light and time and the expanding fabric of the universe itself. In 1929, Edwin Hubble published an analysis showing that the recession velocity of a galaxy was directly proportional to its distance from us. The further away a galaxy was, the faster it was moving away. This relationship, now called Hubble's law, is one of the most fundamental observations in cosmology. The constant of proportionality, the Hubble constant, has been measured many times by many different methods. Its precise value is still slightly debated, with measurements clustering around 67 to 73 kilometers per second per megaparsec. For every megaparsec of distance, a galaxy recedes faster by about 70 kilometers per second. This sounds gentle. 70 kilometers per second sounds like a quiet speed. But the relationship compounds with distance. A galaxy 10 megaparsecs away recedes at 700 kilometers per second. A galaxy 100 megaparsecs away recedes at 7,000. A galaxy 1,000 megaparsecs away recedes at 70,000 kilometers per second, and the speed of light is approximately 300,000 kilometers per second. Do the arithmetic, and you arrive at a haunting conclusion. Beyond a certain distance, galaxies are receding from us faster than light can travel. This does not violate special relativity. Special relativity prohibits objects from moving through space faster than light. It says nothing about space itself stretching at any rate it pleases. Galaxies beyond the so-called Hubble radius are not moving through their local patches of space at superluminal velocities. They are sitting relatively still, embedded in their own gravitational neighborhoods, while the space between them and us inflates faster than any signal can cross it. The distinction is technical. The consequence is absolute. Light from those galaxies, if emitted today, will never reach us. They are visible only because they used to be closer, because the universe used to be smaller, because the photons we now see left them at a time when the gap between us and them had not yet stretched beyond the reach of light. For a long time, the Hubble radius was thought to be the practical limit of what we could ever interact with. But the truth is even worse, because the universe is not just expanding, it is accelerating. Dark energy, the mysterious component of the universe that drives this acceleration, ensures that the expansion is not slowing down, it is speeding up, and this changes the calculation in a way that turns the gentle limit of the Hubble radius into something far more permanent. It is called the cosmic event horizon. The cosmic event horizon is the distance beyond which light emitted now will never reach us, no matter how patient we are, no matter how long we wait. It sits currently at approximately 16 to 18 billion light years. Anything beyond that horizon is gone, forever sealed away, forever locked behind a wall of expanding space too fast for light to cross. The observable universe extends roughly 46 billion light years in every direction from us, because we can still see light that left distant galaxies billions of years ago when the universe was younger and smaller. But the reachable universe, the volume from which any signal could theoretically still reach us if emitted now, is a much smaller bubble. Approximately 6% of the galaxies in the observable universe still lie within the cosmic event horizon. The other 94% are already beyond reach. We can still see them, because their light from earlier eras is still arriving, but they themselves, as they exist right now, are gone. We cannot reach them. We cannot signal them. We cannot, under any circumstances permitted by the laws of physics as we currently understand them, ever interact with them again. 94%. Out of the estimated 2 trillion galaxies in the observable universe, roughly 1,900,000,000,000 are already beyond our reach. Forever. Each of those galaxies contains, on average, hundreds of billions or trillions of stars. Each of those stars may host planets. Each of those planets may host chemistry, biology, life, intelligence, civilization. Whatever exists out there, whatever ever has existed out there, whatever ever will exist out there, is sealed away from us behind a wall that grows wider every second. and the situation is not stable. It is getting worse. Every passing year, the cosmic event horizon shrinks slightly closer to us, in the sense that more and more galaxies cross from the reachable set into the unreachable. Galaxies that today still lie within 16 billion light-years will, in coming eons, cross beyond that boundary as the expansion of space accelerates further. The reachable universe is contracting. The accessible cosmos is shrinking. Every century, entire galaxies that today we could theoretically have visited at light speed slip past the threshold and become permanently lost to us. This is the universe we live in, not an open frontier waiting to be explored, not an abundance of destinations spread before us like cities on a map, a small contracting bubble of accessibility surrounded by a wall of expanding space, with the wall closing slowly but inexorably around us as the cosmos continues its accelerating runaway toward dispersal. The galaxies are out there. We can see them. We can count them. We can study them in extraordinary detail through telescopes that grow more powerful every year. And every observation that confirms their existence simultaneously confirms that we will never reach them. The very knowledge of their existence is the limit of our relationship with them. Beyond knowing they are there, beyond seeing their light, there is nothing else we will ever be able to do. Chapter 9. The Long Goodbye. Imagine, then, what happens next. The Milky Way and Andromeda, locked in their gravitational embrace, continue to fall toward one another for the next several billion years. The exact details of the collision remain a subject of active scientific investigation, with the most recent measurements suggesting that a full merger is most likely to occur somewhere between 4 and 7 billion years from now. The two galaxies may collide directly. They may glance off one another and then return for a second pass. They may take many billions of years to fully merge. Whatever the specifics, the outcome is the same. The Milky Way and Andromeda will combine. Their stars will mingle. Their dark matter halos will fuse. Their central black holes will spiral toward one another and eventually merge in a colossal release of gravitational waves that will ripple outward across the universe. The result will be a single new galaxy. Astronomers have already named it, in the cheerful, informal way that astronomers sometimes name future events that none of them will ever witness. Andromeda, a portmanteau of the two parent galaxies. Andromeda will be a giant elliptical galaxy, its delicate spiral structure long since destroyed by the violence of the merger, its stars orbiting in random directions around a massive central core. The elegant arms of the Milky Way and Andromeda will be gone. The dust lanes, the star-forming regions, the gentle rotation of the disk, all of it will be erased in the gravitational chaos of the collision. What remains will be a vast bloated sphere of older, redder stars, slowly fading over tens of billions of years as new star formation gradually shuts down. Around the same time, the Triangulum galaxy, currently the third largest member of our local group, will likely merge with Andromeda as well. The smaller dwarf galaxies will be consumed one by one, tidally disrupted, their stars absorbed into the larger structure. By the time the dust settles, the local group will no longer exist as a collection of distinct galaxies. It will exist as a single enormous elliptical galaxy, alone in the surrounding darkness, the only large structure within billions of light years. And here is the heartbreaking part. By the time Andromeda has fully formed and stabilized, the rest of the universe will have changed in ways that no observer inside the new galaxy will be able to fully reconstruct. because cosmic expansion will have continued during all those billions of years. Every galaxy outside the local group will have receded further. The Virgo cluster, currently 54 million light-years away, will have drifted hundreds of millions of light-years further. The Coma cluster, the Hercules superclusters, every gathering of galaxies that currently lies beyond the local group will have moved past the cosmic event horizon. Their light will have redshifted to longer and longer wavelengths until it slips below the detection threshold of any conceivable instrument. The filaments of the cosmic web connecting our region to neighbouring structures will have thinned and dispersed. The walls between voids will have grown so faint that they no longer count as structure at all. The universe outside the local group will have effectively vanished. A civilization arising inside Andromeda at that distant future epoch, perhaps 50 or 100 billion years from now, will look outward into the sky and see nothing. Not nothing in the sense of an empty night. Nothing in the sense of an absolute structural emptiness extending in every direction beyond the boundaries of their own galaxy. They will see their galaxy's stars, brilliant and beautiful, filling their sky with this dense band of light. But beyond the edges of Andromeda, in every direction, only blackness. Their most powerful telescopes, no matter how advanced, will find nothing to look at. No distant galaxies, no quasars, no background glow from earlier eras of cosmic history. The cosmic microwave background itself, currently filling the sky as a faint radio whisper from the Big Bang, will have redshifted to wavelengths so long that no instrument can detect it. The very evidence of the Big Bang will have been carried beyond the horizon by the expansion it set in motion. The future civilization will have no way of discovering that the universe was once filled with other galaxies. They will have no way of inferring that an event called the Big Bang ever occurred. Their cosmology will be wrong. Not because they are stupid, not because they lack the intelligence to figure it out, but because the universe will have systematically removed the evidence they would need. They will look at their single, isolated galaxy floating in infinite black space and conclude, reasonably, that the universe consists of one galaxy in an empty void. That is what their data will tell them. That is what their telescopes will show them. They will have no way of knowing any different. They will be wrong. We are not. We are alive at the privileged moment when the universe still wears its history on its sleeve. We can see the cosmic microwave background. We can map the large-scale structure of the cosmic web. We can observe galaxies at distances of billions of light-years and reconstruct, with extraordinary precision, the story of how the universe evolved from its hot, dense beginning to its current state. We are the last generation in some sense who will ever have the full picture. The universe is in the process of erasing its own history, hiding its own origin, carrying the evidence of its own past beyond the horizon of any future observer. This is not metaphor. This is not philosophy. This is the direct, calculable, observationally confirmed future of the cosmos we inhabit. Dark energy is real. Cosmic acceleration is measured. The expansion rate is known. The math is not ambiguous. The universe is headed toward a state of ultimate isolation, in which every galaxy is alone, in which the very memory of cosmic structure is lost, in which the only thing remaining is dark and silence, and the slow, patient draining away of every form of energy and information. And we are the witnesses. We are the brief window of perceiving creatures who happen to exist at the moment when the cosmos can still be seen for what it really is. After us, the universe will close its books. The galaxies will go dark to one another. The story will end not with a bang or with a whimper, but with a slow erasure of the evidence that there was ever any story at all. Chapter 10. The Arithmetic of Alone. Let us take stock of what we've learned so far, because the picture is starting to come together, and it is not the picture most people are taught. The universe is enormous. The observable portion of it spans roughly 93 billion light-years from one edge to the other. It contains, by best current estimates, approximately 2 trillion galaxies. Each galaxy contains, on average, somewhere between 100 million and 1 trillion stars. The total stellar population of the observable universe runs into the sextillions. The number of planets is probably even larger, the number of moons larger still. By every reasonable measure, the universe is a place of staggering abundance. And yet, of those 2 trillion galaxies, 94% are already beyond our reach, forever. Light from them might still arrive from earlier eras, but anything happening in those galaxies right now is unreachable, unsignalable, untouchable in any physical sense. We can know they exist, but we cannot interact with them. We can see their past, but we cannot influence their present. Of the remaining 6%, the vast majority are still so far away that any meaningful round-trip communication would take hundreds of millions or billions of years. A message to a galaxy 50 million light-years away takes 50 million years to arrive, and a reply takes another 50 million years to come back. The exchange spans 100 million years total. No civilization, no species, no continuous line of inheritance has ever lasted that long on this planet. The dinosaurs flourished for roughly 170 million years before their sudden extinction. Modern humans have existed for perhaps 200,000. The exchange of a single hello and a reply with a galaxy 50 million light-years away would consume more than 500 times the entire duration of our species so far. Within the small subset of galaxies that lie close enough for round-trip communication times measured in mere thousands or tens of thousands of years, the numbers shrink rapidly. We're essentially limited to galaxies in our own local group, and the local group is small, a few large galaxies, 100 or so dwarfs, all gravitationally bound, all destined to eventually merge. Once the merger is complete, the local group becomes Andromeda, a single galaxy, and the rest of the universe falls beyond the horizon. Within Andromeda, of course, there will still be other stars, billions and billions of them, possibly some with planets, possibly some with life. Within a single galaxy, the laws of physics permit communication and even travel on timescales that biology might survive. A civilization that managed to spread itself across its own galaxy could, in principle, exchange messages and even ships across distances measured in tens of thousands of light-years. The Milky Way could, in principle, be unified by a sufficiently patient and long-lived civilization. Maybe Andromeda will be too, but between galaxies there is nothing. Beyond the local group, every other gathering of stars is travelling away from us, and they will continue travelling away until they pass beyond the horizon and disappear forever. We will never go to them. They will never come to us. We will never know what they were, what they built, what they discovered, what they dreamed. Whatever wonders exist out there, whatever questions they have answered, whatever beauty they have witnessed, all of it is sealed away from us by walls of expanding space that grow taller every day. This is the arithmetic of cosmic loneliness. The number of galaxies in the universe does not change the calculation. It only makes it more bitter. 2 trillion galaxies, and we're alone with our family of 140. 2 trillion possibilities, and 94% of them have already been removed from the realm of contact. 2 trillion neighbours, and we will live and die without ever once exchanging a meaningful word with any of them. The cosmos was not built for connection. Whatever forces shaped it, whatever physical processes determine the values of its constants and the structure of its laws, those forces did not produce a universe that wants its inhabitants to find one another. They produced a universe that scatters its structures across volumes too vast for any signal to bridge, then accelerates that scattering with every passing aeon, then ensures that the very evidence of other structures eventually disappears from the perception of any observer left behind. This is not a flaw in the universe. This is not a problem awaiting a solution. This is what the universe is. It is, at the deepest level, an architecture of loneliness. And our place inside that architecture is to be one small, flickering exception to the dominant rule of emptiness. We are a campfire on a beach so wide that even the next campfire is too far to see. We are a candle in a cathedral with no walls. We are, in the only meaningful sense, alone, even when the night sky overhead glitters with the photographs of trillions of other islands of light. Chapter 10.5 The Silent Neighbours. There is a question that humanity has been asking since the moment we realized the universe contained other galaxies. The question of whether we are alone. It is one of the oldest questions our species has ever framed, and it is, at the same time, one of the youngest. We have only had the conceptual framework to ask it properly for about a century, since the moment Edwin Hubble's measurements made it impossible to deny that the Milky Way was just one galaxy among many. The conventional way to address this question is to think about the Drake equation, that famous formula proposed by the astronomer Frank Drake in 1961, which attempts to estimate the number of communicative civilizations in our own galaxy. The equation multiplies together a series of factors: the rate of star formation, the fraction of stars with planets, the fraction of planets with conditions suitable for life, the fraction of suitable planets where life actually arises, the fraction of life-bearing worlds that produce intelligence, the fraction of intelligent species that develop the capacity for interstellar communication, the average length of time such civilizations remain technologically active. Plug in optimistic numbers and the equation suggests that the galaxy should be teeming with civilizations. Plug in pessimistic numbers and the equation suggests we might be the only one. The truth is that we do not know the values of most of those factors with any precision. The equation is, in its current form, less a calculation than a way of organizing our ignorance. But here is the part that the Drake equation does not directly address. Even if the equation is wildly optimistic, even if every nearby galaxy contains hundreds or thousands of communicative civilizations, the architecture of cosmic distance ensures that those civilizations cannot communicate with each other. They are sealed inside their own galaxies, isolated from every other galaxy by the same intergalactic distances we have been describing this whole time. The space between galaxies turns the question of cosmic loneliness from a probability problem into a topology problem. Even if life is common, the universe is structured to ensure that no civilization ever meets another. Every galaxy is its own quarantine ward. Every civilization that arises inside a galaxy is trapped within that galaxy for the entire duration of its existence. The fact that other galaxies contain other civilizations is, from a practical standpoint, almost irrelevant. They cannot reach us. We cannot reach them. We will live and die without exchanging a single meaningful signal with them. Within a single galaxy, the situation is somewhat better. The distances are still enormous, but they are at least manageable on the timescales civilizations might survive. A signal from one side of the Milky Way to the other takes 100,000 years to travel. That is still long. It is longer than recorded human history, but it is not infinitely long. A patient civilization, one that planned across geological timescales, could in principle communicate across its own galaxy. It could send signals and receive replies, even if the conversation moved at the pace of mountain ranges. But between galaxies, the situation is hopeless. The round-trip time to Andromeda, the closest large galaxy, is 5 million years. That exceeds the typical lifespan of any species in the fossil record. It exceeds the entire span of modern humans by a factor of 25. No biological civilization, no continuous line of cultural development has ever maintained its identity across timescales remotely approaching that range. The dinosaurs lasted longer in terms of biological continuity, but they did not maintain a recognizable culture across that span. Species change, civilizations rise and fall, languages die. The accumulated knowledge of any given period is forgotten or transformed or lost within timescales that are absurdly short compared to the journey time of a signal to our nearest galactic neighbor. This means that even if Andromeda contains a civilization right now, even if they are listening, even if they have built radio telescopes pointed in our direction, the signal we send today will not reach them for 2.5 million years. Whatever civilization receives it will not be the civilization we're trying to talk to. It will be the distant successor or remnant or replacement of that civilization, 2.5 million years removed from the one we knew about when we composed the message. And if they reply, the reply will not reach us for another 2.5 million years. By that point, our own civilization will have transformed beyond anything we could recognize. The conversation cannot happen. The conversation has been outlawed by the architecture of the universe itself. There is a particular kind of grief that comes from understanding this. The grief is not for ourselves. The grief is for what might be out there and what we will never know about. Every galaxy in the universe may contain civilizations. Every civilization may have built wonders we cannot imagine. Every wonder may contain answers to questions we've not yet learned to ask. And all of it is sealed away, not by malice, not by indifference, by the simple fact of how the universe is structured. A civilization in the Virgo cluster might have developed technologies that would transform our understanding of physics. A civilization in the Coma cluster might have solved problems we cannot even articulate. A civilization in some galaxy we will never name, in some cluster we will never see clearly, in some cosmic filament that lies 1 billion light-years from our position, might have, at some point in its history, witnessed beauty or wisdom or experience of a kind that we will never approach. All of it real, all of it possibly happening right now, all of it completely beyond our reach. This is the silence between galaxies, not just an empty silence, a silence full of unheard voices, a silence full of unwitnessed achievements, a silence full of all the cosmic communities that might exist, but that we will never confirm and never meet and never know. And if you are paying attention, this silence is what you're listening to right now, when you look up at the night sky and see the faint glow of distant galaxies and feel, somewhere in the back of your mind, the strange weight of wondering whether anything is out there. Something might be. Something probably is, but the architecture of the cosmos has built walls around them, the same way it has built walls around us. We're not alone in the literal sense. We're alone in every operational sense. And the silence will continue. The silence will deepen as the cosmic event horizon shrinks and more galaxies cross beyond it. The silence will eventually become absolute as the universe ages and the structures recede further into the dark. Whatever civilizations exist now, whatever conversations might in principle be possible, will end up trapped inside their respective galactic prisons, unable to confirm one another's existence, unable to share what they have learned, unable to participate in any kind of cosmic community. This is the universe we live inside. This is the deep structural truth that no future technology can ever undo. We are alone with our own galaxy, and with a small handful of galaxies bound to us by gravity. Everything else is, for all practical purposes, an empty rumour, a glimmer of light from across an unbridgeable distance, suggesting the existence of other minds, but providing no possibility of contact, no possibility of confirmation, no possibility of conversation. The silence between galaxies is not just empty, it is full of unheard others, and that is what makes it the most haunting silence in the universe. Chapter 11. The Tyranny of Light. There is one more thing about cosmic distance that the casual imagination almost never grasps, and it is perhaps the cruelest of all the obstacles between us and the galaxies beyond. It is the tyranny of light itself. Light is fast. By every standard of human experience, it is unimaginably fast. It crosses the distance from Earth to the Moon in about 1¼ seconds. It crosses the distance from Earth to the Sun in roughly 8 minutes. It reaches the edge of our solar system in a matter of hours. Within a single human lifetime, you could send a signal across our entire galaxy several times over, theoretically, if you had a sufficient transmitter. Light is the universe's express courier. Nothing physical moves faster, and light is hopeless at the scale of intergalactic distance. When you send a message at the speed of light to Andromeda, the message takes 2.5 million years to arrive. You do not get to wait for an answer. You do not get to live to hear the reply. The civilization that sent the message will be unrecognizable or extinct by the time any response could possibly return. The round trip exceeds 5 million years. That is longer than our entire genus has existed. Communication across intergalactic distances is not a conversation. It is a message in a bottle thrown across a sea so wide that even the fastest current in the universe cannot bring an answer back within any time frame that anyone alive could meaningfully experience. And as we've already seen, the distances only get worse beyond Andromeda. 54 million light-years to the Virgo cluster, 320 million to the Coma cluster, 600 million to the Hercules superclusters, 2 billion light-years to the most prominent walls of galaxies that form the largest visible structures in the cosmic web. The further out you look, the longer the round trip. At some point the numbers stop being numbers and start being categories. They become, in their literal meaning, eternal. A round trip of 1 billion years is not a delay. It is a sentence. Worse, even one-way messages have a problem. Light, like every other form of electromagnetic radiation, can be redshifted by the expansion of space. As a photon travels through expanding space, its wavelength is stretched, its frequency drops, its energy decreases. Over short distances within our solar system, this effect is too small to measure. Over the scale of a galaxy, it is detectable only with sensitive instruments. Over the scale of intergalactic distances, it becomes significant, Over the scale of the cosmic event horizon, it becomes catastrophic. A radio signal sent today at a frequency of, say, 1000 megahertz will arrive at a galaxy 1 billion light-years away with its frequency reduced. The exact amount depends on the rate of cosmic expansion during the transit. At 1 billion light-years, the wavelength will have stretched by approximately 7%. At 5 billion light-years, the wavelength will have nearly doubled. At 10 billion light-years, the wavelength will be more than twice what it started as. Approaching the cosmic event horizon, the wavelength stretches without bound. The signal effectively disappears into the noise floor of the cosmos, its energy diluted across so many cycles that no instrument could ever distinguish it from random background fluctuation. The universe does not just delay your messages, it eats them. It stretches them out until they are too faint to detect. It carries them across a wall of expanding space that not only slows them down, but also reaches into them and pulls them apart, frequency by frequency, until the signal vanishes into silence. There is one further problem. The energy required to send a detectable signal over intergalactic distances is staggering. The inverse square law ensures that the strength of any electromagnetic signal drops with the square of the distance. To send a signal that could be detected by a receiver in Andromeda, you would need a transmitter many millions of times more powerful than anything we have ever built. To send a signal that could be detected by a receiver in the Virgo cluster, you would need a transmitter rivaling the output of a small star. To send a signal that could reach the Coma cluster, you would need to convert the energy of a substantial fraction of an entire stellar mass into a focused beam aimed precisely at your intended target. And then you would need to wait 300 million years to see if anyone was listening. This is the tyranny of light. The fastest messenger in the universe is, at the scale of intergalactic distance, almost useless. It is too slow. It is too weak. It is too easily eroded by the expansion of the space it must cross. Even the most powerful signal we could ever conceive of sending would either fail to reach its intended target, fail to arrive within any meaningful time frame, or fail to retain enough energy to be detectable when it got there. The universe has constructed walls of cosmic distance that not even light itself can effectively cross at the larger scales. And these walls are growing. They are growing right now, in this very moment, as you listen to these words. Every second, the wall between us and every distant galaxy gets a little higher. Every second, the universe seals itself a little more tightly into its archipelago of isolated islands of structure. Every second, the dream of cosmic contact recedes a little further into impossibility. This is not a problem we can solve. This is the universe we live in. The tyranny of light is the tyranny of the laws of physics themselves, and those laws are not negotiable. Chapter 11.5 The Structures That Should Not Exist. Before we move on to consider what it means to be alive inside this vast architecture, there is a darker side note that has to be acknowledged. Because the cosmic web, with all its filaments and voids and clusters, is not as orderly as the simple description suggests. There are anomalies. There are places in the universe where the architecture has produced features so enormous that they push against the very assumptions our cosmology is built on. Features so large that, by the standard models of structure formation, they should not exist at all. Features that, when astronomers first detected them, were treated with suspicion and disbelief, and that have since been confirmed by enough independent observations to make denial impossible. The first of these is the Hercules Corona Borealis Great Wall. Discovered through analysis of gamma-ray burst distributions across the sky, the Hercules Corona Borealis Great Wall is, by some measurements, the largest known structure in the observable universe. It is a filament, or rather a complex tangle of filaments, that contains an unusually high concentration of gamma-ray bursts and, by inference, an unusually high concentration of galaxies. Its full extent is staggering. Estimates place its length at approximately 10 billion light-years. Read that again. 10 billion light-years. The structure spans roughly 10% of the entire diameter of the observable universe. It is so vast that light itself, travelling at the absolute speed limit, would need 10 billion years to cross it from end to end. The structure is older, in light travel time, than the planet you're standing on. The problem with the Hercules Corona Borealis Great Wall is not that it is large. The universe contains many large structures. The problem is that, according to the standard cosmological models we use to describe the universe, it should not be that large. The cosmological principle, which is one of the foundational assumptions of modern cosmology, states that on sufficiently large scales the universe should be homogeneous and isotropic, the same in every direction, the same at every place. There should be no concentrations of structure larger than approximately 1,200,000,000 light-years. Beyond that scale, the universe should look statistically uniform. The Hercules Corona Borealis Great Wall is roughly 8 times that scale. It is not supposed to exist, and yet it does, or at least it appears to. Some astronomers have argued that the apparent structure is a statistical artifact of how gamma-ray bursts are distributed and detected. Others have argued that the structure is real, and that our cosmological models need to be revised. This debate continues. But the fact that such a feature has been proposed, and that the data supporting it has so far resisted dismissal, points to something important. The universe, on the largest scales we've ever surveyed, may be even less orderly than our models predicted. The architecture of cosmic structure may include features so enormous that the very idea of a homogeneous cosmos becomes questionable. And the Hercules Corona Borealis Great Wall is not the only candidate. There is the Sloan Great Wall, discovered earlier and somewhat smaller but still vast at over 1 billion light-years long. There is the Huge Large Quasar Group, a concentration of quasars that spans approximately 4 billion light-years, and that, like the Hercules Wall, exceeds the size limits predicted by standard cosmology. There is the Giant Arc, a more recently identified structure of galaxies, arranged in a curve roughly 3 billion light-years long. Each of these features raises the same uncomfortable question. How can structures this large exist if the universe is supposed to be smooth on these scales? The answer, if there is one, may lie in our incomplete understanding of how dark matter behaves at the larger scales, or in subtle features of the initial conditions of the Big Bang that we have not yet fully characterized, or in something even stranger that we have not yet imagined. The point is not to settle the question here. The point is that the universe, even in its largest visible features, is not behaving entirely the way our theories predict it should. There are structures out there that push against the limits of what we thought possible. There are arrangements of matter on cosmic scales that suggest the architecture of the cosmos is more complicated than the simple foam pattern of voids and filaments. And here is the part that connects back to the loneliness. Whatever these enormous structures actually are, whatever processes produced them, whatever their full extent and meaning, we will never visit them. We will never send probes through them. we will never measure them directly with anything more sophisticated than the light that happens to reach us from their constituent galaxies. The Hercules Corona Borealis Great Wall, if it exists, sits at a distance of approximately 10 billion light-years. It is in effect an artifact of the early universe that we're seeing as it was when the cosmos was less than a third of its current age. By the time those photons reached us, the structure itself had already evolved into something different, something we will never be able to observe directly, something that is now permanently beyond the cosmic event horizon. This is the recurring theme of intergalactic distance taken to its larger scale. The universe contains wonders that exceed every expectation, and every one of those wonders is unreachable. The larger structures known to science are by definition the most distant, and the most distant structures are the most thoroughly sealed away from us by the expansion of space. It is almost as if the cosmos has arranged a particularly cruel kind of teasing. It shows us through the patient observation of telescopes that have taken centuries of human effort to build that there is more out there than we could have imagined, and then it informs us through the same instruments that all of it is gone, receding, permanently inaccessible, visible only as a fossil record of an earlier era of cosmic history, when those structures were within the reach of light that has now nearly exhausted its energy in the long trip across expanding space. The universe gives us the view, and then takes away the destination. This is what it means to inherit a universe of accelerating expansion. The vista is unimaginable, the wonders are real, and they are receding from us at every moment, in every direction, with no possibility of ever being approached or interacted with or known beyond what their distant light has already managed to tell us. Chapter 11.8 The Strangest Emptiness. There is one more cosmic phenomenon related to intergalactic emptiness that deserves attention before we move forward, because it represents perhaps the most extreme example of the universe's tendency toward voidness. It is called a supervoid, and it represents the largest example of cosmic emptiness ever directly identified. The most famous of these is the cosmic microwave background cold spot, first detected in detailed studies of the cosmic background radiation in the early 2000s. The cold spot is a region of the sky where the background temperature is measurably lower than the average across the rest of the cosmic microwave background. The temperature difference is tiny, only a few hundred millionths of a degree, but it is statistically significant and persistent across independent observations. For a long time, the origin of the cold spot was a mystery. It was simply too cold for the variations expected by standard cosmological models. Several explanations were proposed. Some suggested it was a statistical fluctuation, an unlikely but possible cold patch produced by the random distribution of temperatures across the sky. Others suggested it might be a signature of new physics, perhaps even of interactions with a parallel universe in some speculative models of cosmology. In 2015, a team of astronomers led by Istvan Zapudi at the University of Hawaii proposed a less exotic explanation. They argued that the cold spot was the imprint of an extraordinarily large cosmic void lying directly between the cosmic microwave background source and our location. As photons from the early universe travel through such a vast underdensity, they lose energy through a process called the integrated Sachs-Wolf effect, in which the gravitational potential of the void changes as the universe expands during the photon's transit. The result is a slight cooling of the photons that pass through the void. The void they proposed, sometimes called the Eridanus supervoid, may be approximately 1,800,000,000 light-years across. That is roughly 2,000 times the diameter of the Milky Way. It is one of the largest cosmic voids ever proposed, and its existence would explain not only the cold spot, but also the otherwise puzzling lack of galaxies detected in surveys of the relevant region of sky. If the Eridanus supervoid is real, and current observations increasingly suggest it is, then it represents an extreme example of cosmic emptiness at the largest possible scale. A region of space nearly 2 billion light-years across with so few galaxies inside it that its presence can be detected through the subtle, cooling effect it imprints on the cosmic background radiation passing through it. But the Eridanus supervoid is only one example. The KBC void, in which our own galaxy may reside, has been proposed by Keenan, Barger and Cowie, based on surveys of the local distribution of galaxies. The KBC void, if it exists, would be approximately 2 billion light-years across with a density roughly 20% below the cosmic average. Our entire galaxy, our entire local group, our entire local supercluster may sit inside a cosmic emptiness on a scale that dwarfs almost every other feature of the nearby universe. Imagine that for a moment. The galaxy you live in, the local group it belongs to, the Laniakea supercluster it is part of, all of it sitting inside a vast region of slightly below average density. A bubble of relative emptiness extending hundreds of millions of light-years in every direction before reaching the denser regions of the cosmic web. Our cosmic neighborhood, the place we call home, may itself be located inside one of the larger voids in the local cosmos. This has interesting implications. It may affect the way we measure the rate of cosmic expansion. It may explain some of the tension between different methods of estimating the Hubble constant. It may mean that our view of the universe is, in subtle ways, biased by the local underdensity we're looking out from. We may be in some sense residents of a cosmic backwater, looking out at a universe that appears more sparsely populated than the cosmic average because our immediate surroundings are themselves below average in density. And there is something poetic, perhaps something painful about that fact. We have spent this entire walk through the void describing the emptiness between galaxies as the dominant feature of the universe. And it turns out that we ourselves may be living inside one of the larger emptinesses. We're not just surrounded by intergalactic void. We're surrounded by an unusually large patch of intergalactic void. Even by the standards of an already overwhelmingly empty universe, our cosmic neighborhood is, in some sense, one of the lonelier places one could find oneself. The implications of this for any future intergalactic ambition are not subtle. If we live inside a supervoid, then the journey from our position to the denser regions of the cosmic web, the regions where galaxies cluster more thickly and where filaments converge, is longer than it would otherwise be. The cosmic horizon that limits our accessible universe extends further from us than it would from a galaxy located in a denser part of the cosmic web. We are, in a sense, even more isolated than the average galaxy. We have further to go to reach almost everything. The universe is, on the whole, an architecture of emptiness, and we are on the whole residents of one of the emptier portions of that architecture. This is the cosmic geography we inherit. This is the address we have been assigned. Chapter 12. The Privileged Moment. It would be easy, having walked this far into the truth, to come away with a feeling of despair. The universe is enormous, mostly empty, expanding, accelerating and engineered in every measurable way to keep its inhabitants apart. The galaxies are unreachable. The civilizations that may exist in other galaxies are unreachable. The very evidence of cosmic structure is being erased by the expansion that defines the universe's future. The cosmos is, by every metric we can apply, profoundly and permanently alone with itself. But there is something else that the long walk through the void can teach us. Something that, at the very edge of despair, opens out into a kind of strange and bewildering gratitude. We are here. We are here at a moment in cosmic history when the universe still wears its evidence openly. The cosmic microwave background still glows in our radio telescopes. The deep field images still reveal galaxies 13 billion light-years away. The cosmic web is still mappable. The local group is still gravitationally bound, with billions of years yet to run before the merger is complete. The Milky Way is still a beautiful spiral, with arms and dust lanes and star-forming regions. Our sun is still in the steady middle of its main sequence life, with billions of years of stable hydrogen burning ahead. Our planet is still alive. Our species is still curious. Our instruments still work, and they reveal to us, year after year, more of the cosmos than any previous generation of humans has ever been able to see. We are alive at the moment when the universe is still legible. Every future generation, every future civilization that arises in this galaxy or any other will inherit a more impoverished cosmos than the one we currently see. The expansion will continue. Galaxies will recede. Evidence of the Big Bang will fade. The cosmic web will dissolve. The future inhabitants of Andromeda, 50 billion years from now, will look out at a sky that contains only their own galaxy, a single isolated structure in an apparently infinite emptiness. They will not be able to do the cosmology we're doing right now. They will not be able to discover what we have discovered. The story of the universe will be hidden from them by the very expansion that defined it. We, by contrast, are the inheritors of a remarkable window. A window through which the universe is still mostly visible, still mostly understandable, still mostly available to careful patient study. Our window will close. Already every passing year galaxies cross beyond the cosmic event horizon. Already, the universe we can ever reach is slightly smaller than it was last year. Already the privileged moment is slipping toward its end. But we're still inside it. We're still inside the cosmological dawn, when the morning light of the universe still illuminates the structures it once gave birth to. The fact that we exist at this moment, the fact that our species has evolved and developed instruments capable of seeing the cosmic story before that story disappears, is not a small thing. It is, in the deepest sense, a kind of cosmic luck. We are here for the closing chapter of the universe's visible self-portrait, and we are still able to read it. And there is something else too. Something that the architecture of cosmic loneliness, for all its terror, cannot quite take away. We are not, despite everything, completely alone. We have the local group. We have Andromeda falling toward us on a confirmed trajectory of slow inevitable merger. We have the Triangulum galaxy. We have the Magellanic Clouds, drifting in their long elliptical paths around our outer halo, our own galaxy's quiet, faithful satellites. We have 140 members of our gravitationally bound family, and none of them are receding from us at the cosmic average. They are travelling with us. They will share whatever fate the Milky Way eventually meets. They are our company, our cosmic relatives, our small loose tribe in the dark. It is a small family. By the scale of the universe, it is almost nothing. But it is a family, and it is ours. and we know it is there. We can map it. We can study it. We can observe its members. We can, given enough time and enough technology, in principle travel to them. There is even, just barely, the possibility that life or intelligence might exist somewhere within our gravitationally bound family, perhaps on a planet in Andromeda or in one of the smaller galaxies that orbit us. The probability is unknown. The numbers are enormous on both sides of the question. But the family is there. The neighborhood, however empty, however vast, is real. And then there is what is inside the Milky Way itself. 200 to 400 billion stars, trillions of planets, an ongoing complexity of stellar populations, nebulae, black holes, neutron stars, exotic remnants, dark matter, magnetic fields, cosmic rays. Our own galaxy is not a single object. It is a vast environment, an entire ecosystem of cosmic phenomena, and we have only begun to explore it. Inside the boundaries of our galaxy, the laws of physics permit travel on timescales that biology can survive. Inside the boundaries of our galaxy, communication on multi-generational timescales is possible. Inside the boundaries of our galaxy, the universe is not yet sealed off from us. The cosmos has, in its strange architecture of isolation, set aside for each civilization that arises within it a small region of approachable existence, a galaxy, a local group, if the civilization is patient enough to consider it. And then, beyond that small reserved region, an infinite expanding emptiness that is permanently out of reach. Maybe that is enough. Maybe a galaxy is enough. Maybe a local group is enough. Maybe the question of whether civilizations elsewhere in the universe exist, whether they have built wonders we will never see or asked questions we will never hear, is a question whose answer is functionally irrelevant to anything we might do with the time we have. Maybe the right response to cosmic loneliness is not despair, but a kind of quiet attention to what is actually accessible, to the planet beneath our feet, to the solar system around us, to the galaxy we live inside, to the family of galaxies we share gravity with, to this small bounded set of structures that the universe, for whatever reason, has placed within our reach. It is, in the end, a great deal. It is more than any single person could ever explore in 100 lifetimes. It is more than any single civilization could ever map in 1 billion years. The accessible cosmos, even after every reduction by the walls of distance and expansion and the tyranny of light, is still enormous. It is still beautiful. It is still full of mysteries we have not begun to address, and it is still ours. Chapter 13. The Quiet Between. There is a kind of silence that exists in the deep places of the universe that no human ear has ever heard and no human will ever hear. The silence between galaxies, the silence of the cosmic voids, the silence of the warm, hot intergalactic medium where a single atom drifts through every cubic meter, and the temperature is high, but the particles too few to carry any heat or any sound. The silence of the space between the Milky Way and Andromeda, that quiet midpoint we visited earlier, where the only objects in any direction are 2 faint smudges of pale light, and the rest is darkness without feature. It is not a silence of the absence of sound. Sound requires a medium. Sound is a pressure wave that travels through air or water or rock. In the intergalactic vacuum, there is no medium dense enough to carry pressure waves of any kind. Sound is not just absent. Sound is impossible. The very concept does not apply. You could detonate the largest bomb ever built at the center of the gap between galaxies, and there would be no sound. There would be no explosion in any sensory sense. There would be a release of energy, photons radiating outward in every direction, but no shock wave, no thunder, no audible signature of any kind. The void would absorb the event without acknowledgement. This is a different kind of quiet than anything we know on Earth. Even in the deepest cave or the highest mountain or the loneliest desert, there is air. There is the hiss of moving molecules. There is the faint roar of your own pulse, the rustle of your clothing, the distant sound of wind moving over rock. The world on Earth is always making noise, even when we cannot hear it. The intergalactic medium makes no noise. It cannot make noise. It is, in the most literal physical sense, the quietest place that exists. And it is everywhere. It is most of the universe. The total volume of the intergalactic medium dwarfs the total volume of all the galaxies combined by factors that human numbers do not honestly express. If you sampled a random cubic meter of the observable universe, you would, with overwhelming probability, sample intergalactic space. The chance of randomly landing inside a galaxy is essentially zero. The chance of randomly landing inside a star is so close to zero that the difference cannot be measured. The chance of landing on a planet, vanishingly low. The chance of landing in a void, effectively one. This is the universe in its truest statistical character. A quiet, vast nothing, occasionally interrupted by rare bright points of structure. The galaxies are the exception. The voids are the rule. When we look up at the night sky on a clear evening, we see the structure, the stars, the Milky Way, the faint smudge of Andromeda. We do not see the voids. The voids do not glow. The voids have no markers. The voids do not announce themselves. They are the dark gaps between the bright places, and our eyes, trained to find structure, focus on the structures and ignore the gaps. But the gaps are most of what is there. The gaps are where the universe lives, in its dominant form. The bright places are the small visible residue of a much larger and quieter reality. To understand the universe truly is to recognize that the silence is the substance. The galaxies are the punctuation marks on a page that is mostly blank. And that recognition, when it finally settles into the mind, has a strange softening effect. The silence is not menacing. The void is not malicious. The expansion is not personal. The universe is doing what it does, on scales that have nothing to do with us, with our hopes, with our fears, with our ambitions. The vastness is not aimed at anything. It simply is. The cosmos has no opinion about whether we feel small inside it, or large, or significant, or insignificant. It does not register our presence at all. It is not measuring us. The terror of cosmic distance, in the end, is a human feeling. The universe itself is not terrifying. It is simply enormous, and quiet, and old, and patient in a way that we, with our short, loud lives, cannot quite hold in our minds without flinching. The terror is in the mismatch between what we are and what the cosmos is. The mismatch will not be resolved. We will remain small and brief, and the universe will remain vast and slow, and the silence between us and every other galaxy will remain as silent as it has always been. But silence is not nothing. Silence can be listened to. Silence can be respected. Silence can be, in its own quiet way, a kind of company. The silence of the cosmic voids is not lonely if you do not need it to be lonely. It is simply what the universe sounds like when there is nothing in it. And there is a kind of dignity to that, a kind of plain, honest fact that does not require any consolation. We are small. We are brief. The galaxies between which we float are unreachable. The cosmic horizon is closing. The story of the universe is, in its largest sense, a story of dispersal and silence, and we are alive inside it, for a small slice of time, able to know all of this and to think about it and to listen, however imperfectly, to the silence that fills almost everything. That is not nothing. That is, in fact, a great deal. Chapter 14. What the Galaxies Remember. Before we draw the long arc of this story to its close, there is one more idea that needs space to breathe. Because so far we have spoken mostly of distance, mostly of emptiness, mostly of the unbridgeable gap between galaxies. We have not yet spoken of what galaxies actually contain, beyond their stars and their numbers, and of why every galaxy in the universe, no matter how remote, holds within it a record of the cosmos that produced it. A galaxy is not just a collection of suns. A galaxy is, in a very real and physical sense, a kind of memory. The chemical composition of a galaxy's stars carries the imprint of every previous generation of stars that ever lived inside it. The first stars in the universe were made almost entirely of hydrogen and helium, the only elements produced in significant quantities by the Big Bang itself. Everything heavier, every atom of carbon, of oxygen, of nitrogen, of iron, of gold, of every element that makes up the planets and the bodies and the chemistry of the world we know, was forged inside the cores of stars, or in the violent deaths that ended stellar lives. When a star dies as a supernova, it scatters its enriched material across the surrounding interstellar medium, where it eventually becomes part of the next generation of stars and planets. Each generation inherits the chemical legacy of the previous, slowly enriching the galaxy with heavier and heavier elements over billions of years. When we look at the spectrum of a star, we can read its chemical composition. We can see which elements are present and in what proportions, and from that we can infer how many generations of stars came before it. We can read the chemical history of the galaxy in the light of its current population. Our own Sun, for example, is a third-generation star. It contains elements that were created in the cores of stars that died long before our solar system formed. Elements that were scattered into the interstellar medium and incorporated into the cloud of gas and dust that eventually collapsed to make our Sun. Every atom of carbon in your body, every atom of oxygen in the air you breathe, every atom of iron in your blood, every atom of calcium in your bones was forged inside a star that died billions of years before the Earth existed. You are, in the most literal physical sense, made of star ash. This is true of every star in every galaxy in the universe. Each one is a chemical archive of the history of the galaxy it inhabits. And the galaxies themselves are archives of the universe's history. The distribution of galaxies in the cosmic web, the way they cluster along filaments and surround voids, encodes information about the initial conditions of the Big Bang. The shape of galaxies, whether spiral or elliptical or irregular, tells us about their merger history, about how violently they have interacted with other galaxies over their lifetimes. The rate of star formation in a galaxy, whether vigorous or quiet, tells us about the gas content and the dynamical state of the system. The presence and mass of central black holes tells us about how the galaxy assembled itself, how matter funneled inward over cosmic time. Every galaxy is a library. Every galaxy is a record. Every galaxy, even the most distant one, the most unreachable one, the one separated from us by walls of expanding space we will never cross, contains the answers to questions about the universe that we're still asking. And we'll never read most of those libraries. Most of them are sealed behind the cosmic event horizon. Most of them are receding too fast for any signal to ever reach us. Most of them will, over the next 100 billion years, slip beyond detection altogether, their light red-shifted into invisibility, their information lost to the expansion that defines our cosmos. The libraries are out there. We can see their outsides. We can count them. We can know that they exist. But the actual content of those libraries, the rich, detailed chemical and dynamical histories that each galaxy carries, will remain, for almost all of them, forever beyond our reading. The information is real. It is preserved inside each galaxy. It is, in principle, recoverable. But we will never recover it, because we cannot reach the galaxies. We cannot send instruments to them. We cannot bring back samples or detailed measurements. We are limited to whatever the photons that reach us can tell us, and photons can only tell us so much. There is a particular grief, perhaps, in this fact. The universe is not stingy with information. The universe is overflowing with information in the form of 2 trillion galaxies, each carrying its own history. But the universe is stingy with access. The information exists, but the cost of retrieving it exceeds anything physics permits. We're surrounded by libraries we'll never enter, by archives we'll never search, by records we will never read. The information is there. The information will remain there, and the information will, for the most part, never reach any mind that could understand it. And yet, we're not entirely cut off. We have our own galaxy, our own local group, our own small accessible cosmos. Those libraries are ours. We can study them. We can read them. We can, given time and technology, learn what they have to teach us. And the lessons they teach us are not limited to local history. The Milky Way and Andromeda, the Magellanic Clouds, the dwarf satellites that orbit our own galaxy, all of these contain information about the broader universe, about the conditions of the early cosmos, about the physical processes that shape all galaxies everywhere. From the libraries we can reach, we can learn things that apply to the libraries we cannot. The accessible universe is a microcosm of the inaccessible one. The same physical laws operate everywhere. The same chemistry happens everywhere. The same kinds of stars are born and live and die everywhere. From the small portion of the universe we can study in detail, we can extrapolate with care to the much larger portion we cannot. In this sense, the architecture of cosmic isolation is not quite as cruel as it first appears. It denies us direct contact. It denies us face-to-face meetings with other galaxies and their inhabitants, if any. It denies us the joy of exchange, but it does not deny us understanding. It does not prevent us from knowing the universe in its broadest patterns, even if we cannot interact with most of its specific contents. The universe is, in some sense, mappable from where we sit. The cosmic web is reconstructable from observations we can make right here. With telescopes that fit inside spacecraft we can build and launch, with the resources of a single planet. The story of cosmic evolution is, despite everything, available to us. We can know things. We can know vast things. We can know things about places we will never visit, about times we will never live to see, about structures whose existence vastly exceeds anything we can ever directly experience. And the knowing itself, is a kind of communion with the cosmos, not a communion we can verify by reply, but a communion all the same. We're looking out at the universe and understanding it, however imperfectly. And the universe, in its quiet, inhuman way, is letting us. That may be the most generous thing the cosmos has ever done for us. Not to bring us close to the other galaxies, not to make us neighbours with the distant structures of the cosmic web, but to allow us, through the patient work of science, to understand the place where we live, even though so much of that place is permanently out of reach. Chapter 15. The Inheritance of Distance. There is something that needs to be said, finally, about what it means to inherit a universe like this one, about what it means to be the kind of creature that can know, at all, about the architecture of cosmic loneliness, about the strange responsibility that comes with being aware, even briefly, of the place we have been placed. Other forms of life on this planet, every other species, lives without any of this knowledge. The trees outside your window do not know that the galaxy they belong to is one of 2 trillion. The animals in the forest do not know that the night sky above them is filled with the light of structures so distant that even light needs millions of years to bring news of them. The microbes in the soil do not know anything about cosmic expansion or dark energy or the warm-hot intergalactic medium. They live, they reproduce, they die, and the cosmos above them is, for all practical purposes, irrelevant to their lives. The vast patient architecture of the universe means nothing to them. Their world is the world of their immediate surroundings, the world of their food and their predators and their mates and their generations. For most of the history of our own species, we were like that too. We looked up at the sky and saw lights. We invented stories to explain the lights. The stories were beautiful and powerful and meaningful in their own way, but they did not penetrate to the actual structure of what we were seeing. The Milky Way was a river or a path or a band of milk spilled across the heavens. The constellations were heroes and animals frozen into the firmament. The distance to the moon, the distance to the sun, the distance to the nearest star, the distance to anything beyond what the unaided eye could see, all of it was beyond the imagination of every culture that ever existed before the development of modern science. And then, in the space of just a few centuries, all of that changed. The telescope was invented. The motion of the planets was mapped. The distance to the moon was measured. The size of the solar system was calculated. The nature of stars was understood. The existence of other galaxies was confirmed. The expansion of the universe was discovered. The age of the cosmos was estimated. The geometry of space was mapped. The cosmic microwave background was detected. The acceleration of cosmic expansion was measured. The cosmic event horizon was calculated. We did all of this. Our species, in the span of a few short centuries, opened a window on the universe that no previous form of life on this planet had ever opened. We saw for the first time what we are actually living inside. We grasped, however imperfectly, the actual scale of the cosmos, the actual nature of cosmic distance, the actual architecture of the universe. And what we saw when we finally looked clearly was this: a universe of staggering vastness, a universe of overwhelming emptiness, a universe in which the structures we are part of are scattered so widely and separated so thoroughly that connection between them is, in any meaningful sense, impossible. A universe that contains us almost by accident in a brief privileged window of cosmic time, with the rest of the cosmos receding from us and the evidence of its history slowly being erased. This is what we have inherited. This is the universe we live inside. And the question, the only real question, is what we do with the knowledge. Some respond to the knowledge with despair. The cosmos is too big. We're too small. Nothing we do matters. Everything we build will be erased. Every signal we send will be lost in the noise. Every civilization that ever arises anywhere will eventually be alone in its own galaxy, surrounded by an expanding darkness, forgotten by the universe that produced it. The despair is honest. The despair is, in some sense, an appropriate emotional response to the facts. The facts are crushing. But despair is not the only response. There is another response, quieter, slower, more difficult, but ultimately more honest, which is this: the fact that the universe is enormous and empty and indifferent and silent does not mean that what we do here, in this small, accessible region of space and time, has no value. The value is not measured against the cosmic scale. The value is measured against the actual texture of our lives. The fact that we are small does not make us nothing. The fact that we are brief does not make our experiences less real. The fact that we are surrounded by an unreachable cosmos does not erase the reachable cosmos we are part of. We have a planet. We have a galaxy. We have a local group of galaxies bound to us by gravity. We have other humans, other minds, other beings on this planet whose lives intersect with our own. We have art and music and science and friendship and love and the strange shifting texture of consciousness itself, which is, by every measure we can apply, the most extraordinary thing the universe has produced in our entire accessible region. The fact that the universe is mostly empty does not change the fact that the small parts of it that are not empty contain everything that has ever mattered to us and everything that ever will. The cosmos, in its strange architecture, has given us a peculiar gift. It has given us the knowledge that we're alone in the way that galaxies are alone, but it has also given us the fact that we are not, in our own immediate experience, alone at all. We are surrounded on this planet by other beings who share our consciousness, our awareness, our small share of time. We have in our hands the materials and the time to make something. We have in our minds the curiosity to keep looking outward, even though most of what we see can never be reached. What we do with this knowledge is, in the end, the only question that matters. And there is no right answer to it. There is only the answer each of us makes by the way we choose to live our lives. But it seems worth saying, here at the close of a long walk through the void, that the proper response to cosmic loneliness might not be despair. The proper response might be a kind of patient, careful attention to the things that are actually within our reach. The proper response might be to take care of the small, accessible portion of the universe we've been given, to make of it whatever beauty and understanding we can, and to leave behind, for whatever future inheritors arise from this small bright planet, a record of what it was like to be alive at this particular moment, in this particular galaxy, in a universe that was already mostly silent and would become more silent still. The cosmos will continue, the galaxies will recede, the light of the early universe will fade beyond the horizon of any future observer. The evidence of the Big Bang will eventually no longer exist for anyone to read. The story of cosmic structure will, in the end, become a story without witnesses. But we are witnesses now. We see the cosmos when it is still seeable. And whatever we do with that brief witnessing, whatever attention we pay, whatever understanding we gather, whatever stories we tell ourselves about the place we live, those are ours. Those are the privilege of the moment. The universe, in its quiet, vast architecture of distance, has somehow produced creatures who can know the architecture. That is, in some strange and unaccountable way, a kind of miracle. Not a miracle in any supernatural sense. A miracle in the sense of something so unlikely and so beautiful that it deserves to be recognized as remarkable. The cosmos is mostly empty, the cosmos is mostly silent, and yet, in this one small corner of it, for this one small slice of time, there is a creature looking back at the cosmos and trying to understand what it is. That creature is us. That is what we are, here, now, in this brief privileged window between the dawn of cosmic structure and the long, slow fade into final silence. And that, perhaps, is enough. Chapter 16. The long settling. It would be wrong to end this story without coming back to the basic facts one last time, because the facts are what hold the story together. Without the facts, the story is just sentiment. With the facts, the story is something more durable, something that the listener can carry away and turn over later, in the quiet moments before sleep, or in the long stretches of solitary thought that everyone passes through eventually. So let us return to the facts in the slow, careful way that they deserve. The universe is approximately 13.8 billion years old. It began in a state of extreme density and high temperature that cosmologists call the Big Bang. From that beginning it has been expanding, and the rate of expansion has not been constant. In the very earliest moments after the Big Bang, the universe underwent a period of rapid inflation that smoothed out the initial conditions and set the stage for everything that followed. After inflation, the universe continued to expand, but at a slower rate, gradually cooling as space stretched and the energy contained within it became more dilute. For the first several 100,000 years, the universe was an opaque plasma. Matter and radiation were tightly coupled, and photons could not travel freely. Then, approximately 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with protons to form neutral atoms, and the radiation that had been trapped in the plasma was finally released. That radiation is what we now detect as the cosmic microwave background, the oldest light in the universe, still arriving at us from every direction nearly 14 billion years later. In the millions and billions of years that followed, gravity began the slow work of assembling structure out of the slight density variations that had been imprinted on the early universe. The denser regions pulled in more matter from their surroundings. The less dense regions lost their matter to their denser neighbours. Over time, the universe grew lumpy. Stars formed, galaxies formed. Galaxy clusters formed. The cosmic web emerged, with its filaments and walls and nodes and voids. For a few billion years after the formation of the first galaxies, the expansion of the universe continued to slow down as matter pulled gravitationally on itself. The deceleration was gentle but real. Cosmologists in the mid-20th century expected, more or less, that the universe would either continue expanding forever at an ever-decreasing rate, or that gravity would eventually halt the expansion altogether and pull everything back into a final crunch. That expectation collapsed in 1998. In the late 1990s, two independent teams of astronomers studying the brightness of distant Type 1, a supernovae, made a discovery that overturned half a century of cosmological assumptions. The universe was not decelerating, it was accelerating. Some mysterious component was pushing space apart faster and faster, overcoming the gravitational pull of all the matter the cosmos contained. That mysterious component was named dark energy. Its origin and nature remain to this day two of the deepest unsolved problems in physics. But its existence and its effect are confirmed beyond any reasonable doubt. Dark energy is what drives the cosmic expansion we now observe. It is what carries galaxies away from one another at accelerating speeds. It is what defines the cosmic event horizon, the boundary beyond which no signal can ever reach us. It is what guarantees that the universe will continue to expand, faster and faster, for the entire foreseeable future of cosmic history. And it is what ensures that the galaxies of the universe, with the exception of those bound together in gravitationally tight groups, will continue to recede from one another until they vanish one by one beyond the horizon of any observer. This is the universe we live in, 13.8 billion years old, expanding, accelerating, mostly empty. Filled with 2 trillion galaxies, 94% of which are already beyond our reach, heading toward a future of progressive isolation, in which the cosmic structure that defines our current epoch will dissolve, in which the evidence of the Big Bang will fade from any future observer's perception, in which each remaining gravitationally bound group of galaxies will end up alone in an expanding darkness. And we are here, now, at a moment when the universe is still visible, at a moment when our species has just barely developed the instruments needed to see what is actually out there. At a moment when, for the first time in the history of life on this planet, the actual architecture of the cosmos is comprehensible to creatures who happen to live on its surface. We are alive at the privileged moment. The window is open, the universe is legible, and we are reading it. How long the window will remain open depends on how you measure the question. Within a few billion years, our sun will leave the main sequence and enter its red giant phase. Within 5 billion years, our sun will swell to encompass the orbit of the Earth, and our planet, if it is still here, will be vaporized by the expanding solar atmosphere. Long before that, the Earth will become inhospitable to life as we know it, as the sun gradually brightens and the surface temperature of our planet climbs beyond the bounds that liquid water can survive. Our species, if we are still around in any recognizable form, will have to either leave the planet or perish along with it. Within a few billion to 10 billion years, the Milky Way and Andromeda will complete their merger, depending on which probability estimate proves correct, and the new combined galaxy Andromeda will begin its long evolution toward the eventual fading of star formation. Within 100 billion to 150 billion years, every galaxy beyond the local group will have receded beyond the cosmic event horizon. By that point, Andromeda will be alone in its own observable universe, with no other galaxies visible to its inhabitants, if any remain. Beyond that, the timescales become almost too long to discuss. Stars will continue to form for trillions of years, then star formation will gradually shut down as the gas reserves of the galaxy run out. The last red dwarf stars will burn for hundreds of billions of years before they too exhaust their fuel and fade to cold black dwarfs. Eventually, on timescales of trillions and quadrillions and quintillions of years, the universe will become a place of cold, faint stellar remnants, drifting in expanding emptiness. Black holes will continue to exist for far longer, slowly evaporating through Hawking radiation over timescales that defy any reasonable description. And then, eventually on timescales so vast that the human numerical system has no honest way to express them, even the black holes will be gone. The universe will become finally a thin, cold soup of decayed particles, expanding forever, with no structure, no stars, no galaxies, no observers, nothing. This is the long settling, the end state of the universe as our current physics predicts it. A slow, patient extinction of every structure, every flame, every form of energy or information, the architecture of cosmic loneliness taken to its ultimate conclusion. We will not be there to see it. Nothing capable of seeing it will be there. The universe will end alone, the way it spends most of its history alone, the way it has, in some sense, always been alone, behind the brief, bright illusion of structure that defined its first 100 billion years. But we're alive in those first 100 billion years. We're alive in the brief, bright window when the cosmic story is still being told. We're inside the small portion of cosmic history when galaxies and stars and planets and minds are still possible. The long settling has not yet begun in earnest. The universe is still young in its own slow, patient way. The window is open. The view is, for now, magnificent. We have time. Not all the time in the world, but enough time to do something. Enough time to notice. Enough time to learn. Enough time to share with one another the strange privilege of being briefly aware of a cosmos that is itself, in the largest sense, simply running its quiet, vast course. Chapter 17. A last walk before sleep. Let us then take one more walk before this story ends. A slow walk, in no particular hurry. A walk that follows the contours of everything we have learned, without trying to fix or argue or conclude anything beyond what the universe itself has already laid out for us. Begin on this planet, the planet you are listening from right now. A small rocky world orbiting an average yellow star in the middle of an unremarkable arm of an ordinary spiral galaxy. The Earth, roughly 4.5 billion years old, roughly 12,000 kilometers in diameter, currently inhabited by an estimated 8 million species, one of which is the species of you. The species that has, in the last few thousand years, developed agriculture, writing, mathematics, science, and the instruments needed to look outward at the cosmos and begin to understand what surrounds us. Step outward from the Earth. The Moon, roughly 400,000 kilometers away, the closest natural body in the universe. Beyond the Moon, the rest of the inner solar system, the orbits of the planets, each one a different kind of world, each one with its own conditions, its own history, its own strange beauty. Mercury, scorched and airless, locked in a slow rotation around the Sun. Venus, choked with carbon dioxide, its surface hot enough to melt lead. Mars, cold and red and quiet, a planet that may once have been warmer and wetter. The asteroid belt scattered with rocky debris. Jupiter, vast and gaseous, with its great red storm older than any human civilization. Saturn, ringed and elegant, with its dozens of moons. Uranus and Neptune, ice giants on the outer edge of the solar system. The Kuiper Belt, a wide disk of icy bodies beyond Neptune. The scattered disk, with its strange long elliptical orbits. The Oort cloud, an immense spherical halo of icy fragments that extends outward to perhaps a light year from the Sun, marking the gravitational boundary of our solar neighborhood. Step beyond the Oort cloud. You are now in interstellar space, the region between stars. The nearest other star, Proxima Centauri, is about 4.2 light-years away. Slightly further, Alpha Centauri A and B, a binary pair of sun-like stars. Beyond them, other nearby stars scattered through the solar neighborhood. Each one is a sun. Each one may have its own planets. Each one is so far away that any signal sent at the speed of light takes years to cross the gap. Step further. Beyond the solar neighborhood, the nearby region of our own galactic arm, the Orion arm where our sun resides, the Sagittarius arm and the Perseus arm, the two arms that flank ours. the dense central bulge of the galaxy, where the supermassive black hole at the heart of the Milky Way sits, currently inactive but capable of bursts of feeding that briefly light up the galactic core. The disk of the galaxy, 100,000 light-years across, full of stars and gas and dust and the slow, orbital motions that have been turning for billions of years. The halo of the galaxy, a sparser region of older stars and globular clusters surrounding the disk. The dark matter halo, an even larger invisible envelope of gravitationally interacting material that extends far beyond the visible boundaries of the galaxy. Step beyond the Milky Way. You are now in intergalactic space. The first thing you encounter, drifting nearby, are the Magellanic Clouds, the closest companion galaxies, orbiting our own. Beyond them, the rest of the local group spread across 10 million light-years of mostly empty space. Andromeda, our great peer, 2.5 million light-years away. Triangulum, slightly further. Many smaller dwarf galaxies scattered through the volume. Step beyond the local group. You are now in the vast intercluster void. The next significant gathering of galaxies, the Virgo cluster, sits 54 million light-years away. Beyond Virgo, other clusters, other superclusters, the Coma cluster, 320 million light-years away. The Hercules superclusters even further. The cosmic web begins to unfold around you, with its filaments and walls and voids and nodes. Step further still. The cosmic web continues outward, in every direction, on scales that begin to defy any sense of place. You pass clusters and voids and filaments and walls. Each region looks broadly similar in its structure but is filled with different specific galaxies. The universe, at scales of hundreds of millions of light-years, becomes statistically homogeneous, the same kind of structure repeating everywhere, the same kinds of voids, the same kinds of filaments, the same kinds of galaxies clustered along the filaments, step to the very edge of what we can see. The observable universe ends at a boundary roughly 46 billion light-years from us. Beyond that boundary the universe continues, but its light has not yet reached us. The light from those distant regions left them so long ago, and the universe has expanded so much in the meantime, that the photons are still in transit and may never arrive. Some of them never will arrive. The cosmic event horizon, 16 to 18 billion light-years away, is the boundary beyond which any light emitted now will never reach us. We can see beyond the event horizon because we can see light from earlier eras, but anything beyond the event horizon as it currently exists is forever sealed away. This is the walk, from the Earth to the edge of what we can ever know, through every scale of cosmic structure, through every level of cosmic distance. And the thing to notice, the thing to carry away from the walk, is how much of the walk is empty. The Earth is small, the Moon is far, the solar system is mostly vacuum, the interstellar space between stars is mostly vacuum, the intergalactic space between galaxies is even more vacuum. The voids between filaments are vast empty bubbles. The cosmic web itself, the largest pattern in the universe, is mostly the empty spaces between the thin walls of structure. At every scale, from the local to the cosmological, the universe is dominated by the absence of matter, the absence of structure, the absence of any form of company. We are tiny bright exceptions to an enormous rule of emptiness. Our planet, our solar system, our galaxy, our local group, all of them are small bright places in a universe that is, on the whole, dark and quiet and almost completely empty. This is what we live inside. And there is, in the end, a kind of peace in accepting it. The architecture of cosmic loneliness is not personal. The universe is not rejecting us. The universe is not punishing us. The universe is not lonely itself, because the universe is not the kind of thing that can be lonely. The universe simply is what it is, vast and empty and patient and indifferent and beautiful in its own strange, inhuman way. And we are alive inside it, briefly, in a small bright corner of a small bright galaxy, surrounded by other small bright structures that are themselves separated by oceans of emptiness so wide that we will never cross them, and we are aware, and we are looking out, and we are, for a brief flickering moment, witnesses to the cosmos that produced us. That is what we are. That is, perhaps, enough. Closing. If you have stayed with this story all the way to the end, thank you. Thank you for spending this long, quiet stretch of time walking through the void with me, listening to the slow accumulation of facts and reflections and reckonings, allowing the scale of the cosmos to settle into the corners of your mind that ordinary thought does not usually reach. This kind of attention is rare. The world we live in does not encourage it. The fact that you have given it, here, for these hours, is something the algorithm cannot quantify, but that the universe, in some indifferent way, has nonetheless received. The space between galaxies is the most terrifying distance in the universe. We have spent this whole journey establishing why. We have walked through the great deception of the photograph, the staggering size of a single galaxy, the journey to Andromeda, and the gravitational embrace that defines our cosmic family, the quiet structure of the local group, the absolute emptiness of the intergalactic medium, the foam architecture of the cosmic web, the impossibility of intergalactic travel under any known physics, the wall of the cosmic event horizon, the long settling of cosmic isolation that defines our universe's future. We have walked through it all, and what we have found on the other side of all that walking is something that the original sense of terror does not quite capture. The universe is enormous. The universe is mostly empty. The universe is, in every meaningful sense, structurally arranged to keep its inhabitants apart. All of that is true. None of that can be unmade by any technology or any hope. But the universe also contains, in this small corner of its vast architecture, a planet on which something improbable has happened. The matter of this planet has organized itself, over billions of years of slow patient evolution, into forms that can perceive the cosmos. Forms that can ask questions. Forms that can build instruments to extend their senses beyond the limits of their biology. Forms that can, in the brief windows of their individual existence, hold in mind something like the actual shape of the universe they inhabit. We are those forms. We are the perceivers. We are the askers. We are the brief flicker of awareness inside an otherwise unaware cosmos, and the fact that we exist at all, at this particular moment of cosmic history, is the strangest and most unaccountable thing in the entire story we've just told. The galaxies are far. The galaxies will remain far. The universe will continue to expand, to accelerate, to scatter its structures further and further apart until the long settling carries them all beyond the reach of any future observer. None of that will change. None of that can be argued with. But here, in this small bright corner, on this small bright planet, for this small bright stretch of time, there is something happening that is not happening in the voids. There is attention. There is curiosity. There is the slow, patient effort of trying to understand what surrounds us. There is in the end a kind of light that the cosmic voids do not contain, even though the voids are full of stretched out photons drifting toward nothing. That light is ours, briefly, imperfectly, improbably, but ours. And so, as we draw this long walk to a close, let me offer one final thought. The space between galaxies is enormous, and we will never cross it. The cosmos is mostly empty, and we will never fill it. The universe is heading toward a state of permanent isolation, and we cannot stop it. All of that is true, and yet, the very fact that we know all of this, that we've been able to walk this far into the truth and look it in the face, is itself a kind of triumph. Not a triumph of conquest, not a triumph of mastery, a quieter triumph. The triumph of understanding what is, even when what is not what we might have hoped for. The night sky above you contains, in its faint scattered points of light, an enormous number of stars. Most of them are in our own galaxy. A few are in nearby galaxies, including the faint smudge of Andromeda visible on dark autumn evenings. Behind those visible lights, in the vast emptiness that the human eye cannot perceive, there are 2 trillion other galaxies. Most of them are unreachable. All of them are real. When you go to sleep tonight, after these words have ended and the story has wound down to its quiet close, remember, just for a moment, what is overhead. Remember the architecture you live inside. Remember that the universe is vast and empty and silent and indifferent. And remember too that for this small flickering moment, you are alive inside it, on a small rocky planet, in a small bright galaxy, in a small gravitationally bound family of galaxies, in a corner of the cosmos that has produced, by some quiet miracle of organization, the brief possibility of awareness. You are awake. The universe, in its largest sense, is not. And for just a little while longer, before sleep comes to settle the day, you have the privilege of holding all of this in your mind, however imperfectly, however briefly. That is enough. Sleep well. The galaxies will still be there in the morning, at the same enormous distances, doing what they have always done. The universe will continue its slow, patient course, and tomorrow, if you would like, we can take another walk together into another corner of the cosmos and try once more to understand what surrounds us. Until then, rest. Be kind to yourself. The space between galaxies is enormous, but the space between you and the people you love is small, and it can be crossed in the time it takes to say a few words. The voids will keep their silence, the galaxies will keep their distance, the cosmos will keep its long, slow course toward whatever it is becoming, and you, here, now, in this small, bright moment, are part of all of it. A witness, a perceiver, a briefly awake fragment of the universe looking back at itself. That, in the end, is the most extraordinary fact this story has had to offer. Not the size of the cosmos, not the emptiness of the voids, not the unreachable distance of the galaxies. The fact that any of it is knowable at all. The fact that, in this one corner of this one galaxy, the universe has briefly opened a window through which it can see itself. Through us. Through you. Through this small, slow act of listening. Thank you for staying with me to the end. Good night, traveller. Sleep deeply. And when you wake, remember that the cosmos, for all its terrifying emptiness, has somehow found a way to be witnessed. That, perhaps, is the only thing about the universe that is not lonely after all. One last thing. Before this story finally ends, if you are listening to this in the dark hours of the night, and the weight of what we have walked through together is settling on you, the way deep cold settles on a stone, remember this. The distance between galaxies is enormous and permanent, but the distance between you and the morning is short. The distance between you and rest is small. The distance between you and the people who care about you, however far they may seem in the late silence of an empty room, is closable in the time it takes to dial a number or open a door or simply remember that they exist. Those distances are human distances. They are not cosmic distances. They are crossable. They are the part of the universe that has been left within your reach. Use them. Do not let the silence of the voids convince you that the silences in your own life are equally permanent. The cosmic silence is real, but it is far away, and the warmth of this small bright planet, the warmth of this small bright moment, is closer than anything the voids could ever take away from you. Good night again. Sleep deeply. The galaxies will still be there in the morning, at the same enormous distances, doing what they have always done. And you, here, will still be the small remarkable thing that, for a little while longer, gets to know about them.